Hello there, and welcome to Science for Sleep, where curiosity settles in softly and the universe takes its time explaining itself, one quiet idea at a time. Tonight, we're going to drift through something so large it almost feels impossible to hold in the mind, yet so familiar that it's been hanging above our heads for as long as humans have looked up. We're going to talk about galaxies, not just one or two, but all the many, many islands of stars we've found so far, scattered across the deep, dark ocean of space. Before we begin wandering too far, let me ask you something simple and gentle. Where are you listening from tonight? Are you tucked into a quiet room, sitting by a window, or maybe lying somewhere that feels just a little softer than the rest of the world? And what time is it where you are right now? Is the day winding down, or has the night already wrapped itself around your corner of the planet? It's a nice thought, isn't it? That while we're talking about distant galaxies separated by billions of light years, we're also quietly connected here, in this small moment, across time zones and everyday lives. If you find this little journey calming, or even just a pleasant way to let your thoughts slow down after a long day, you might consider giving the video a like or subscribing to this cozy corner of science. It helps this gentle space reach others who might also be looking for something peaceful to listen to as the world fades into the background. Now, there's no rush at all. Nothing here needs to be memorized or solved. You can simply let the ideas pass by like clouds, or like stars sliding slowly across a night sky. So, let's ease into it. When most people hear the word galaxy, a particular image often comes to mind. A bright, swirling spiral, glowing softly in shades of white, blue and gold, maybe with a dark centre and delicate arms stretching outward like a cosmic pinwheel. It's a beautiful picture, and it's not wrong, but it's also just one small glimpse into something far larger and more varied than our imagination usually allows. A galaxy, at its simplest, is a massive collection of stars, gas, dust, and something we can't see but know is there, called dark matter, all held together by gravity. That definition sounds neat and tidy, but the reality is anything but small or simple. Each galaxy can contain millions, billions, or even trillions of stars, and around many of those stars there may be planets. And on some of those planets, who knows what might be happening right now, in their own quiet rooms, under their own unfamiliar skies. The idea that the universe is filled with countless galaxies is something we take for granted today. We see it in images from space telescopes and hear numbers like 200 billion galaxies in the observable universe, and our brains sort of nod politely and move on. But for most of human history, no one thought that way. For a very long time, the night sky was not a window into an endless cosmic city. It was a ceiling. A dark one, yes, and dotted with lights, but still something that felt close, contained, and somehow centered around us. If you go back a few thousand years, people looked up and saw patterns. They connected stars into shapes, animals, heroes, and stories. The sky became a canvas for mythology, navigation, and calendars. The Milky Way itself, that faint misty band stretching across the night, was seen as a river, a road, or a trail left behind by gods or spirits. No one imagined it was made of countless distant suns, let alone that it was just one among many similar structures scattered across a much larger universe. Even when early telescopes came along in the 1600s, they didn't immediately reveal the true scale of things. Galileo pointed his simple telescope at the Milky Way and discovered that the hazy glow was actually made of stars. Too many and too faint to see with the naked eye. That was a big step. It turned the sky from a flat backdrop into a deep field layered with light. But it still didn't answer the bigger question. Were all the stars in existence part of this one great system, or was there more beyond it? For centuries, fuzzy patches of light in the sky were known as nebulae. The word itself just means cloud. Some of these turned out to be clouds of gas and dust inside our own galaxy, places where stars are born or where they leave behind glowing remains. But others were different. They were faint, soft, and often had a smooth, rounded shape. Through small telescopes, they looked like pale smudges, stubbornly refusing to resolve into individual stars. One of the most famous of these was the Andromeda Nebula. You can actually see it with the naked eye on a dark, clear night if you know where to look. For a long time, people argued about what it was. Some thought it was a cloud of gas within our own galaxy. Others suspected it might be something far more distant, perhaps even a system of stars in its own right. The problem was that there was no reliable way to measure how far away it was. Without distance, size is just a guess. As telescopes improved, so did the debate. By the early 1900s, astronomers were split into two main camps. One side believed that the Milky Way was essentially the entire universe. In their view, all stars, all nebulae, all cosmic structures were contained within this single enormous system. The other side thought the universe was much larger, and that at least some of these nebulae were actually separate galaxies, far beyond the boundaries of our own. This disagreement came to a head in 1920 in what is now called the Great Debate. Two astronomers, Harlow Shapley and Heber Curtis, presented their opposing views to an audience in Washington, D.C. Shapley argued for a big Milky Way that contained everything. Curtis argued for a universe filled with many galaxies, what were sometimes called island universes. At the time, neither side had definitive proof. The data simply wasn't good enough yet. The breakthrough came a few years later, thanks to another astronomer named Edwin Hubble. Using a powerful telescope at Mount Wilson Observatory, Hubble studied stars in the Andromeda Nebula and identified a specific type of star called a Cepheid variable. These stars brighten and dim in a regular pattern, and the timing of that pattern can be used to calculate how bright the star truly is. By comparing that true brightness to how faint it appears from Earth, you can figure out how far away it must be. When Hubble did the math, the result was astonishing. Andromeda was not a small cloud inside the Milky Way. It was far, far beyond it. So far, in fact, that it had to be a separate galaxy, containing its own vast collection of stars. In one careful measurement, the universe suddenly became much bigger. From that moment on, the night sky changed in a fundamental way. Those faint smudges were no longer just curiosities. They were entire galaxies, each one a massive structure on a scale that makes our own Milky Way feel both grand and somehow very small at the same time. As more telescopes were turned toward the sky, the number of known galaxies began to grow. Astronomers started cataloguing them, photographing them, and trying to make sense of their shapes and behaviours. It became clear that galaxies come in different forms, not just the neat spirals people often picture. Some galaxies are shaped like flattened disks with winding arms, full of gas, dust, and active star formation. Others are more like giant glowing balls, with stars moving in all directions and very little new star birth happening inside them. And some don't seem to follow any tidy pattern at all. They look stretched, twisted, or broken, often because they've been pulled apart by close encounters with other galaxies. Each type tells a story about its past. A spiral galaxy suggests a long, relatively calm history, where stars and gas have had time to settle into an orderly rotation. A large, smooth, elliptical galaxy often hints at a violent past, the result of multiple mergers where smaller galaxies crashed together and blended into one. Irregular galaxies can be signs of ongoing interactions, cosmic traffic accidents still playing out over millions or billions of years. As the decades passed, the tools of astronomy kept improving. Photographic plates gave way to electronic detectors. Ground-based telescopes grew larger and more precise, and eventually telescopes were launched into space, free from the blurring effects of Earth's atmosphere. The Hubble Space Telescope, named after the same man who helped prove that other galaxies exist, became one of the most important eyes we've ever turned toward the universe. When Hubble pointed at what looked like empty patches of sky and took long exposures, it revealed something remarkable. Those dark areas were not empty at all. They were filled with tiny, faint points of light. Each one of those points was a galaxy, often so distant that its light had been travelling for billions of years before reaching us. The image became known as the Hubble Deep Field, and later even deeper views followed. These deep surveys changed the way we think about the cosmos again. They suggested that wherever you look, no matter how small the patch of sky, you're likely to find galaxies stacked behind galaxies, layer upon layer, stretching back toward the edge of what we can observe. Counting them, however, turned out to be surprisingly difficult. Galaxies don't come with neat labels or boundaries. Some are bright and obvious, others are faint and diffuse, barely standing out from the background. Some overlap along our line of sight, making it hard to tell where one ends and another begins, and beyond a certain distance, galaxies become so faint that even our best telescopes struggle to detect them. Still, astronomers have tried. By combining deep images with careful statistical methods, they've estimated that the observable universe contains on the order of hundreds of billions of galaxies, and that's just the part we can see. The universe might extend far beyond the observable limit, carrying even more galaxies with it into regions we will never be able to observe directly. At this point, it can start to feel a little overwhelming. Hundreds of billions of galaxies, each with billions of stars, each star potentially with its own collection of worlds. The numbers grow so large that they stop feeling like numbers and start feeling more like a kind of background noise, a vastness that's easier to sense than to calculate. So it can help to come back just for a moment to something smaller and closer. Our own galaxy, the Milky Way. This is the one we live in, the one that appears as that pale band across the night sky. It's a barred spiral galaxy with a central bar of stars and sweeping arms that curve outward. Our solar system sits in one of those arms, about halfway between the centre and the outer edge. From our position inside it, the Milky Way is hard to see as a whole. It's a bit like trying to understand the shape of a forest while standing among the trees. We rely on careful measurements, radio observations and models to piece together its structure. But even with all that, there's still a sense of mystery about our own galactic home. Orbiting around the Milky Way are smaller companion galaxies called dwarf galaxies. These are much less massive, sometimes containing just a few million stars, but they play an important role in the story of galaxy formation. Over time, many of them are slowly pulled in by the Milky Way's gravity, stretched into long streams of stars and eventually absorbed. Our galaxy grows, not just by forming new stars, but by quietly gathering and blending with its smaller neighbours. This process isn't unique to us. Across the universe, galaxies are constantly interacting. They pass by each other, tug on each other with gravity, and sometimes collide and merge. These events can trigger bursts of star formation, feed central black holes, and dramatically reshape the galaxies involved. Even though everything is moving at incredible speeds, these changes unfold so slowly that from a human perspective, the cosmos feels almost frozen in place. Yet, when we look far enough away, we're also looking back in time. Light takes time to travel. The farther a galaxy is, the older the image we see. Some of the most distant galaxies we've detected appear as they were when the universe was very young, just a few 100 million years after the Big Bang. They look smaller, clumpier, and more chaotic than many nearby galaxies, giving us clues about how these massive structures first formed. With newer telescopes, like the James Webb Space Telescope, we're now pushing even further. Webb is designed to see infrared light, which allows it to detect extremely distant galaxies whose visible light has been stretched to longer wavelengths by the expansion of the universe. Early images from Webb have already revealed galaxies that formed earlier and appear more developed than many scientists expected. Each new observation adds a piece to the puzzle, and sometimes rearranges the puzzle entirely. So, when we talk about all the galaxies we've found so far, we're really talking about a moving target. The list is always growing. New surveys scan the sky, new instruments pick up fainter and more distant objects, and every so often something shows up that doesn't quite fit into our existing categories, reminding us that the universe still has plenty of surprises tucked away in its quieter corners. It's also worth remembering that what we call a galaxy is in many ways a human-made label. Nature doesn't draw sharp lines around these systems. There are star clusters that blur into small galaxies. There are streams of stars that are the remains of galaxies long since torn apart. There are vast halos of dark matter extending far beyond the visible stars, shaping how galaxies move and interact in ways we can only infer indirectly. In that sense, our catalogues and classifications are like a map drawn in pencil. Useful, detailed and impressive, but always open to revision. As our view of the universe becomes sharper, the map gets redrawn. If you let your mind linger on that for a moment, it can feel oddly comforting. The idea that even on the largest scales imaginable, things are still being discovered, still being refined, still being understood a little better than they were yesterday. The universe isn't a finished book. It's more like a story that keeps adding pages, quietly and patiently. Long before anyone had a telescope to press against their eye, long before the word galaxy meant anything more than a soft band of light across the night, people were already living under a sky that quietly shaped how they understood the world. If you imagine stepping outside on a clear night thousands of years ago, far from any city lights, you would see something that most of us rarely experience now. The sky would not be black with a few scattered points of light. It would be alive. Stars would fill it in every direction, bright and faint, clustered and alone, with a pale, glowing streak stretching from one horizon to the other. That streak, the Milky Way, was not a scientific object. It was a presence. For early humans, the sky was not something distant and detached. It was woven into daily life. It marked the passing of seasons, guided journeys, and carried stories that explained where people came from and where they might go when life on the ground came to an end. The stars were not distant suns. They were ancestors, animals, campfires of the gods, or holes punched in the fabric of the night by curious spirits. In many ancient cultures, the Milky Way was seen as a river. In parts of China, it was the Silver River, separating two lovers in the sky who could only meet once a year. In ancient Greece, it was said to be milk spilled from the goddess Hera as she pushed away the infant Hercules. Among some indigenous peoples of the Americas, it was a path of souls, a road the dead travelled on their way to the next world. These ideas were not born from measurements or calculations. They came from long nights of looking up, from the simple human need to make sense of something vast and mysterious. Without any instruments, the sky still offered patterns. Constellations emerged as ways to organise the chaos of points into recognisable shapes. A hunter here, a bear there, a scorpion crawling low near the horizon. These shapes helped people remember where certain stars would appear at different times of the year. And that, in turn, helped them predict changes in weather, animal migrations, and planting seasons. The sky became a calendar written in light. Even then, there was a sense that the stars were not all the same. Some were brighter, some flickered. A few wandered slowly against the fixed background, earning the name planets, which comes from a Greek word meaning wanderer. But no one imagined that the faint, misty glow of the Milky Way was made of countless stars, let alone that it was just one part of something even larger. The idea of a structured universe, arranged in layers or spheres, began to take shape in ancient civilizations. In Mesopotamia, astronomer priests recorded the movements of stars and planets on clay tablets. They saw the sky as a reflection of divine order, something that could be read for omens and guidance. In ancient Egypt, the stars were linked to the afterlife. Pharaohs were believed to ascend to the heavens and join the imperishable stars that never set, circling the sky endlessly. The Greeks brought a more philosophical approach. Thinkers like Aristotle imagined the universe as a series of concentric spheres with Earth at the centre. The moon, sun, planets and stars were each embedded in their own transparent shell, rotating around us in perfect, unchanging motion. In this model, the stars were fixed in place, part of a distant but finite boundary of the cosmos. There was no concept of depth beyond that outermost sphere. The universe was large, but it was contained. This geocentric view, with Earth at the centre, fit well with everyday experience. The ground beneath your feet feels still. The sky above appears to move. It was a simple, elegant way to explain what people saw, and it held on for centuries. Even as more detailed star catalogues were created, the basic structure of the cosmos remained the same in the human imagination. In ancient China, astronomers mapped the sky with remarkable care. They divided it into regions and recorded new stars, comets, and unusual events. Their records are some of the oldest continuous astronomical observations we have, yet even with this level of detail, the stars were still seen as part of a single, overarching system connected to the fate of the empire and the balance of forces on Earth. Across the world, in the Americas, the Maya built observatories and developed complex calendars based on the movements of celestial bodies. They tracked cycles that spanned decades and even centuries. The sky was not just beautiful or mysterious, it was precise, it followed rules. But those rules were still thought to operate within a single, unified cosmic dome. What's striking is how long this basic idea lasted. Even as instruments improved and mathematical models became more refined, the universe remained, in most minds, a single grand structure with the stars fixed in a distant shell and the Milky Way as some kind of atmospheric or celestial phenomenon within it. When the first telescopes appeared in the early 1600s, they did not immediately shatter this worldview. Galileo Galilei's telescope was simple by modern standards, but it revealed things no one had ever seen before. The moon had mountains and craters. Jupiter had moons of its own. Venus went through phases like the moon, which supported the idea that it orbited the sun. Perhaps most importantly for our story, Galileo turned his telescope toward the Milky Way. What had looked like a smooth, cloudy band to the naked eye resolved into countless faint stars. This was a revelation. The Milky Way was not a mist or a glow. It was made of stars, packed so closely together that their light blended into a continuous streak. That discovery added depth to the sky. It suggested that the universe was not just a flat dome with lights attached to it, but a three-dimensional space filled with stars at different distances. Still, even then, those stars were all assumed to belong to one vast system. The Milky Way was not one galaxy among many. It was the galaxy, though that word was not yet used in that way. The term galaxy itself comes from the Greek word for milk, a reference to the Milky Way. For a long time, it simply meant that glowing band of stars. There was no need for a plural form, there was only one. As telescopes improved over the next few centuries, astronomers began to notice more of those fuzzy patches scattered across the sky. Some were clearly clusters of stars. Others were clouds of glowing gas. But a subset remained puzzling. They were smooth, often oval-shaped, and stubbornly refused to resolve into individual stars, no matter how powerful the telescope. These objects were all lumped together under the name nebulae. The word did not imply anything specific about their nature. It just meant they were cloudy or fuzzy. Among them was the Andromeda Nebula, the Great Nebula in Orion, and many others catalogued by astronomers like Charles Messier, who was actually more interested in comets and wanted a list of things that were not comets so he wouldn't get confused during his searches. Messier's catalogue, still used today, is a fascinating snapshot of a time when astronomers were carefully mapping the sky, but did not yet know what they were truly looking at. Some of the objects on his list are star clusters within our own galaxy. Some are clouds of gas, and some are entire galaxies, though that fact would not be confirmed until long after Messier himself was gone. Even as late as the 1800s, the idea that the universe might contain multiple galaxies was still controversial. Astronomers like William Herschel, who built some of the largest telescopes of his time, tried to map the structure of the Milky Way by counting stars in different directions. He imagined our galaxy as a flattened disk of stars with the sun near the centre. In his view, the nebulae were likely distant star systems, perhaps similar to the Milky Way, but the evidence was not strong enough to convince everyone. Others argued that these nebulae were simply part of our own galaxy, perhaps clouds of gas where stars were forming. Without a reliable way to measure distances beyond a certain point, it was almost impossible to settle the question. The sky offered light, but it did not offer a built-in ruler. This uncertainty created a kind of cosmic ambiguity. The universe could be enormous, filled with countless star systems like our own. Or it could be large but still fundamentally singular, with everything contained inside one grand structure. Both ideas were compatible with the limited data available. Meanwhile, the night sky continued to play its role in everyday life. Sailors used the stars to navigate across oceans. Farmers watched the rising and setting of certain constellations to decide when to plant and harvest. Time itself was often measured by the sky, through sundials during the day and the positions of stars at night. In this way, the stars were practical as well as profound. They were tools as much as they were symbols, and yet, even in their practical use, they carried a quiet sense of wonder. The idea that these tiny points of light could guide a ship across a dark, trackless sea speaks to a deep trust in the order of the cosmos. One of the most interesting aspects of this period is how the sky felt both intimate and distant at the same time. People named individual stars. They told stories about them. They tracked their movements with care. But the true scale of what they were looking at remained hidden. It's a bit like standing on a beach and watching waves roll in, without realizing that the ocean stretches thousands of kilometers beyond the horizon. The surface is visible. The depth and breadth are not. As the 19th century turned into the 20th, technology began to catch up with curiosity. Photography allowed astronomers to capture long exposures of the sky, revealing faint objects that the eye could not see. Spectroscopy, the study of light split into its component colors, made it possible to analyze the composition of stars and nebulae. These tools added new layers of information to the simple act of looking up. When astronomers examined the light from different nebulae, they found that some glowed with the distinctive signatures of hot gas, while others had a more star-like spectrum. This suggested that not all nebulae were the same kind of object. Some were indeed clouds of gas within our galaxy. Others might be something else entirely. The stage was set for a shift in understanding, but the shift itself had not yet fully arrived. The sky, as seen from Earth, still looked much the same. The Milky Way still arced overhead on dark nights. The fuzzy patches still hovered in the background, their true nature just out of reach. There is something quietly beautiful about that moment in human history, a time when the universe was on the verge of becoming much larger in our minds, but had not yet done so. A time when people stood under the same stars we see today, unaware that those stars were just a tiny sampling of a far greater cosmic population. If you imagine one of those early astronomers standing beside a telescope made of wood and brass, carefully adjusting lenses and mirrors, you can almost feel the anticipation. Each new observation had the potential to reveal something never seen before. The sky was familiar, but it was also full of unanswered questions, and those questions were not abstract. They were grounded in what people could see and measure. How far away are the stars? What are those cloudy patches? Is there an edge to the universe? Does it go on forever? These are big questions, but they began with very simple acts. Looking, noticing, writing things down, comparing what you saw tonight with what you saw last year. The night sky before we knew what galaxies were was not a lesser sky. It was the same sky, filled with the same light. What was different was the story we told ourselves about it, the meaning we attached to those points of brightness and those pale streaks of glow. In some ways, that older story was more personal. The sky was closer to human life. It spoke in the language of myths, seasons, and daily rhythms. The modern story, with its billions of galaxies and expanding space, is grander in scale, but also more distant in feeling. Neither story is wrong. They are different ways of relating to the same reality. One through imagination and tradition, the other through measurement and theory. and perhaps that's why it can be nice sometimes to linger in that earlier moment, to think about what it was like to see the Milky Way not as a galaxy, but as a path, a river, or a breath of light across the heavens. To look at Andromeda not as a massive spiral system millions of light years away, but as a quiet smudge, a small mystery waiting patiently to be understood. Because even now, with all our technology and knowledge, the sky still holds that quality. We know more, but we don't know everything. There are still faint points of light in deep images that we can barely explain. There are still questions about how the first galaxies formed, how dark matter shapes their motion, and what lies beyond the edge of what we can observe. So in a way, we are not so different from those early sky watchers. We still stand under the same canopy of stars. We still feel that mix of familiarity and distance. The main difference is that now, when we look at that glowing band of the Milky Way, or that faint smudge of Andromeda, we carry an extra layer of understanding with us. We know that those lights are not just nearby decorations in a small contained universe. They are part of a vast population of galaxies, each one a city of stars, each one moving through space on a slow, quiet journey, shaped by gravity and time. The sky remains the same, but the questions sharpen. How big is the Milky Way really? Where do we sit within it? And what, exactly, are those other faint, stubbornly unresolved patches of light? At the beginning of the 20th century, the universe still felt, at least to most astronomers, like a very large but ultimately singular place. The Milky Way was not just our home. It was thought to be the grand structure that contained everything else. Stars, nebulae, clusters, wandering planets, all of it lived inside one enormous flattened system of light. The sky might be deep, but it was not, in this view, endlessly layered with other worlds like our own. That idea did not fall apart all at once. It unravelled slowly through careful measurements, quiet disagreements, and a growing sense that some of the things we were seeing simply did not fit into the old picture as neatly as we wanted them to. At the heart of the problem was distance. Knowing what something is often depends on knowing how far away it is. A small, nearby object can look very similar to a large, distant one. Without a reliable way to measure cosmic distances, astronomers were left trying to build a map of the universe with no scale bar in the corner. Within the Milky Way, there were methods to estimate distances to nearby stars. One of the oldest is parallax, which relies on the apparent shift in a star's position when observed from different points in Earth's orbit. It is a bit like holding your thumb out at arm's length and closing one eye, then the other. Your thumb appears to jump against the background. The closer it is, the bigger the jump. Stars, however, are so far away that their parallax shifts are tiny, and this method only works for relatively nearby ones. For stars beyond that range, astronomers needed something else. This is where certain types of stars began to play a crucial role, even though no one initially set out to make them into cosmic measuring tools. Among the many kinds of stars in the sky, there is a group known as variable stars, which change in brightness over time. Some of them brighten and dim in a regular, predictable pattern. One particular class, called Cepheid variables, turned out to be especially useful. These stars pulse in a steady rhythm, growing brighter and dimmer over periods of days or weeks. What makes them special is a relationship between how fast they pulse and how bright they truly are. The longer the period, the brighter the star. This relationship was discovered in the early 1900s by an astronomer named Henrietta Leavitt, who worked at the Harvard College Observatory. She studied Cepheid variables in nearby star systems and noticed this clear pattern. Even though she did not live to see the full impact of her work, her discovery became one of the most important tools in modern astronomy. If you can determine how bright a Cepheid star actually is, and then measure how bright it appears from Earth, you can calculate how far away it must be. It is like knowing the wattage of a light bulb and seeing how dim it looks from across a field. The dimmer it appears, the farther away it must be. This method opened up a new layer of the universe. Suddenly, astronomers were not limited to estimating distances within a relatively small bubble around the Sun. They could start measuring distances across much larger regions of the Milky Way and potentially beyond it. At the same time, telescopes were becoming more powerful. One of the most impressive of the era was the 100-inch Hooker telescope at Mount Wilson Observatory in California. When it was completed in 1917, it was the largest telescope in the world. Its size allowed it to collect far more light than any previous instrument, revealing faint stars and details in distant objects that had never been seen before. This telescope would become central to the moment when the Milky Way lost its status as the entire universe. An astronomer named Edwin Hubble began using the Hooker telescope to study some of the mysterious nebulae that had puzzled observers for decades. Among them was the Andromeda Nebula, that faint, elongated patch of light visible to the naked eye on a dark night. Through the big telescope, Hubble could see individual stars within it, something that had not been possible before. As he examined these stars, he identified several Cepheid variables. This was the crucial step. By measuring their pulsation periods, he could determine how bright they truly were. By comparing that to how bright they appeared in his telescope, he could calculate their distance. The result was staggering. Andromeda was not a small object within the Milky Way. It was incredibly far away, far beyond the outer edges of our galaxy. The numbers placed it at a distance of roughly 2 million light-years, though later refinements would adjust that value. Even with uncertainties, the conclusion was clear. Andromeda had to be a massive system of stars in its own right. This was not just a new fact to add to a textbook. It was a fundamental shift in how humanity understood its place in the cosmos. The Milky Way was no longer the whole universe. It was one galaxy among many. The old term island universes suddenly felt very appropriate. Each of these distant nebulae was an island of stars, separated from the others by vast stretches of dark, mostly empty space. Once that door was opened, it could not be closed again. Astronomers began looking at other nebulae with new eyes. If Andromeda was a galaxy, then perhaps many, or even most, of the other fuzzy patches were as well. Over the next few years, more distance measurements confirmed this idea. One by one, objects that had once been thought of as clouds or odd features within the Milky Way were revealed to be separate galaxies, each with its own immense population of stars. The universe expanded in the human mind, not physically but conceptually. The familiar night sky became a foreground layer in a much deeper cosmic scene. Around this same time, another discovery was quietly reshaping the story even further. As astronomers studied the light from distant galaxies, they noticed something strange. The spectral lines, which act like fingerprints for the elements in stars, were shifted toward the red end of the spectrum. This shift, known as redshift, suggested that these galaxies were moving away from us. The farther away a galaxy was, the more its light was shifted. This relationship became known as Hubble's law. It implied that the universe itself was expanding, with galaxies moving away from each other as space stretched between them. This idea added a new layer of meaning to the fact that the Milky Way was just one galaxy among many. Not only were there countless other galaxies, but they were all part of a dynamic, evolving universe, one that had a history and possibly a beginning. But even before the full implications of cosmic expansion settled in, the realization that our galaxy was not unique was enough to change the tone of astronomy and, in a quieter way, human self-perception. For centuries, Earth had been removed from the center of the universe. First, the Sun took that place. Then, our solar system became just one among many. Now, even our galaxy was no longer special. It was one member of a vast population, drifting through an enormous, mostly unseen expanse. It is worth pausing on how quickly this transformation happened. Within a few decades, the universe went from being a single, structured system to a nearly incomprehensible ocean of galaxies. This shift did not happen in isolation. It was part of a broader change in how science approached the cosmos. Astronomy was becoming more quantitative, more dependent on precise measurements and physical laws. The sky was no longer just a place of lights and patterns, it was a laboratory. Yet, for all the numbers and graphs, the emotional impact of this new picture was hard to ignore. The idea that every faint smudge in a deep image might be a galaxy, similar in scale to our own, carries a kind of quiet weight. It suggests a universe that is not just big, but richly populated. Imagine standing on a hill at night, looking out over a city. You see countless lights, each one marking a building, a street, a place where people live and move and think. Now imagine that every point of light in the sky is not a building, but a city of stars, and that beyond the lights you can see, there are many more, fading into the distance. That is the kind of mental leap astronomers had to make in the early 20th century. As the number of known galaxies grew, so did the need to organise them. Astronomers began to classify galaxies by their shapes and structures. The most famous of these classification systems was developed by Hubble himself. He arranged galaxies into a diagram that looked a bit like a tuning fork. On one side were elliptical galaxies, smooth and rounded, ranging from nearly spherical to more elongated shapes. Along the stem and arms of the fork were spiral galaxies, including barred spirals like the Milky Way, with a straight bar of stars through the centre and arms winding outward. At the far end were irregular galaxies, which did not fit neatly into either category. This system was not just a way to sort pictures. It hinted at deeper questions about how galaxies form and evolve. Were these shapes stages in a life cycle? Did galaxies change from one type to another over time, or were they born into their forms and largely stayed that way? As observations improved, it became clear that interactions between galaxies played a major role in shaping them. Galaxies could pass close enough to pull on each other with gravity, stretching out streams of stars and gas. They could collide and merge, forming larger, more massive systems. These events could trigger waves of new star formation, or feed the growth of central black holes. All of this added to the sense that galaxies were not static islands, but active participants in a much larger cosmic story. The realization that the Milky Way was just one galaxy also raised a more personal question, even if it was not always stated out loud. If our galaxy is not special, then what about our sun, our planet, us? This question has been asked in many forms throughout history. Each time science has revealed that we are not at the centre of something, it has prompted both discomfort and curiosity. The galaxy shift was another step along that path, but it also brought a kind of connection. If the laws of physics are the same everywhere, then the processes that shape our galaxy also shape others. Stars form, live and die in distant galaxies just as they do here. Elements forged in ancient supernovae spread through space, becoming part of new stars and planets. In that sense, the universe feels less like a collection of separate, unrelated systems, and more like a single, vast, interconnected whole. As the 20th century progressed, new tools continued to deepen this picture. Radio telescopes revealed structures in galaxies that were invisible in visible light. X-ray observatories detected hot gas and energetic processes near black holes. Infrared telescopes saw through dust to uncover hidden regions of star formation. Each new window on the universe showed that galaxies were even more complex and varied than their simple optical images suggested. And yet, the basic shift remained. No matter how detailed our understanding became, the fundamental idea stayed the same. The Milky Way was one of many. There is something quietly grounding about that realization. It can make everyday concerns feel small, but it can also make them feel part of something larger. Our lives unfold on a tiny planet in one spiral arm of one galaxy, among billions of others. That fact does not diminish the significance of those lives. If anything, it places them within a wider shared context. When you look up at the night sky now, especially from a place dark enough to see the Milky Way clearly, you can carry both perspectives at once. The old one, where that glowing band is a familiar presence, a river of light across the darkness, and the newer one, where that river is the edge-on view of a vast disk of stars, gas and dust, similar in many ways to countless other disks scattered across the universe. Somewhere out there, in the direction of that faint smudge we call Andromeda, another galaxy is moving slowly toward us. Over the next few billion years, it and the Milky Way will drift closer, drawn together by gravity. Eventually they will merge, their stars passing mostly harmlessly by one another, their shapes reshaping into something new and larger. That future collision is a reminder that even on the grandest scales, change is constant, just very slow. The moment when the Milky Way stopped being the whole universe was not just a scientific milestone, it was a shift in perspective. It took the sky from being a single, enclosed system and opened it into a deep, layered expanse filled with structures similar to our own, each one with its own history and future. Long before the phrase became part of scientific language, the idea behind it had already been quietly forming in the minds of people who spent their nights looking through eyepieces and sketching what they saw by hand. The term island universes sounds poetic, but it was originally a very practical way of describing a serious possibility. What if those faint misty patches scattered across the sky were not clouds or nearby clusters at all? What if they were entire systems of stars, separated from us and from each other by vast stretches of empty space, like distant islands in a dark cosmic sea? At first, this idea felt almost too large to take seriously. The Milky Way itself was already enormous by any reasonable measure. It contained hundreds of billions of stars and spanned tens of thousands of light years. To suggest that there might be many other structures like it, each one just as big and just as complex, was to suggest a universe of a scale that went far beyond everyday intuition. Still, the sky kept offering hints. When astronomers studied the distribution of nebulae across the heavens, they noticed something interesting. These fuzzy objects were not scattered evenly. Many of them appeared far from the plane of the Milky Way. If they were part of our galaxy, you might expect them to be concentrated along the same flattened disk where most of the stars are. But instead they seemed to form their own pattern, one that did not quite line up with the structure of the Milky Way. This observation did not prove anything on its own, but it added to the growing sense that something was different about these objects. At the same time, improvements in spectroscopy were revealing more about the light coming from nebulae. When light from a star or a galaxy is spread out into a spectrum, it shows dark or bright lines that correspond to specific elements. Hydrogen, helium, oxygen and other elements each leave their own signature. By comparing these signatures, astronomers could tell whether an object's light looked more like that of a hot gas cloud, or more like that of a collection of stars. Some nebulae showed clear signs of glowing gas with strong emission lines. These were likely clouds within the Milky Way, lit up by nearby stars. But others had spectra that looked more like starlight, a blend of many stellar signatures rather than the sharp lines of a gas cloud. That suggested they might be made of stars, not just gas. Again, this was not enough to settle the matter, but the pieces were beginning to line up. The phrase island universe was used to capture this possibility. If each of these nebulae was its own galaxy, then the universe was not a single continent of stars, but an archipelago, with countless star systems scattered across a much larger expanse. The idea had supporters and skeptics. On one side were astronomers who felt that the Milky Way was already so large that it could easily contain all known objects. They argued that nebulae were simply distant parts of our own galaxy, perhaps clouds of gas or unresolved star clusters. On the other side were those who pointed to the evidence of distribution and spectra, and suggested that these objects were too different, too spread out to belong to a single system. The disagreement was not just about facts, it was also about what felt reasonable. The human mind has a way of resisting sudden jumps in scale. It took time to accept that Earth is not the centre of the solar system. It took time to accept that the Sun is just one star among many. Accepting that our entire galaxy might be just one of countless others was another step along that path. In the early 1900s, this tension came to a kind of public focus. Astronomers were not shouting at each other in the streets, but they were publishing papers, giving talks and debating interpretations. The data was improving, but it was still incomplete. The sky offered light, but not always clarity. One of the key problems remained distance. Without knowing how far away these nebulae were, it was impossible to say how big they truly were. If a nebula was inside the Milky Way, it might be relatively small. If it was far beyond, it could be as large as our entire galaxy or larger. This is where the work on variable stars, especially Cepheids, began to play a larger role. Once astronomers realized that these stars could be used as reliable distance markers, they started searching for them in as many places as possible. Finding a Cepheid in a nebula was like finding a signpost with a readable number on it. It turned a vague smudge into something that could be measured. But spotting these stars was not easy. They are not especially bright compared to some of the other stars in a galaxy, and at great distances even powerful telescopes struggle to resolve them. This meant that only the largest and clearest nebulae could be studied in this way at first. Among those, Andromeda stood out. As more detailed observations came in and distance measurements began to place Andromeda far beyond the Milky Way, the idea of island universes shifted from a bold hypothesis to a serious conclusion. Andromeda was not an odd feature in our galaxy, it was a galaxy. Once that realization took hold, it had a kind of ripple effect. If Andromeda was a galaxy, then many of the other nebulae with similar appearances and spectra were likely galaxies too. The sky, which had once seemed like a single system, now appeared to be layered with these distant star cities, each one its own gravitationally bound community. The first great realization was not just that there were other galaxies, it was that the universe itself had a structure on a much larger scale than anyone had previously imagined. Before this, the largest meaningful structure in the cosmos had been the Milky Way. Beyond it was, in most models, either nothing or a relatively simple backdrop of fixed stars. Now, the Milky Way became one node in a vast network. This shift changed the kinds of questions astronomers asked. Instead of focusing only on the structure and contents of our own galaxy, they began to wonder about the population of galaxies as a whole. How many are there? How are they distributed? Do they form patterns? Do they interact? Early surveys began to map the positions of known galaxies across the sky. What they found was not a random sprinkling. Galaxies tended to cluster. They formed groups and larger clusters, bound together by gravity. Between these clusters were vast regions with relatively few galaxies, areas that would later be called cosmic voids. Even at this early stage, the universe was beginning to look less like a uniform fog of stars and more like a complex large-scale structure. There was also a growing awareness that galaxies themselves were not isolated in a permanent sense. Gravity connects them across enormous distances. Over time, galaxies can fall toward one another, interact and merge. The island metaphor is useful, but it has its limits. These islands are not fixed in place. They drift, slowly but steadily through the cosmic sea. The idea of island universes also carried a philosophical weight. It suggested that the processes that shape our own galaxy might be common throughout the cosmos. Star formation, supernova explosions, the creation of heavy elements, the formation of planets, all of these things could be happening in countless other places. This did not immediately lead to widespread speculation about life elsewhere, at least not in scientific circles, but it did create a framework in which such questions could eventually be asked in a more grounded way. From a cultural perspective, the realization that there are many galaxies added another layer to humanity's changing sense of its place in the universe. We were not just in a solar system that was not special, or in a galaxy that was not unique. We were in one of many galaxies, in a universe that seemed to have no obvious center at all. This can sound unsettling, but it can also be seen as a kind of connection. The same physical laws apply in Andromeda as they do here. The same elements that make up our bodies were forged in stars long ago, and those same elements exist in stars and galaxies across the observable universe. In that sense, the idea of island universes does not separate us from the rest of the cosmos. It places us within a much larger family. As more galaxies were identified, astronomers began to notice differences among them. Some were rich in gas and dust, with bright blue regions where new stars were forming. Others were dominated by older, redder stars and showed little sign of ongoing starbirth. Some had well-defined spiral structures. Others were smooth and rounded. These observations hinted at the idea that galaxies might have life stories of their own. They could be born, grow, interact, change, and perhaps even fade over time. The first great realization, then, was not a single moment, but a transition. It was a period during which the sky changed from being a single stage to being a deep field filled with many stages, each one hosting its own ongoing drama of matter and energy. What makes this period especially interesting is how it blends old and new ways of thinking. On the one hand, astronomers were using cutting-edge technology and mathematical tools. On the other hand, they were still guided by simple acts of observation, comparison, and careful note-taking. They were, in a sense, doing what humans have always done when faced with something unfamiliar. They were looking for patterns, testing ideas, and slowly building a story that could make sense of what they saw. The term island universe eventually faded from everyday scientific use, replaced by the more precise word galaxy. But the image it evokes remains useful. It captures that moment of expansion in human understanding, when the universe suddenly grew from a single grand structure into a vast collection of them. It also captures something about how galaxies are arranged. They are not evenly spread like grains of sand on a beach. They are grouped, clustered, and connected by the invisible pull of gravity. They form filaments and walls, leaving large empty spaces in between. The universe, on its larger scales, looks less like a smooth ocean and more like a complex web. This large-scale structure was not fully understood at the time of the first great realization, but the seeds of that understanding were there. Once you accept that there are many galaxies, the next natural step is to ask how they are arranged and why. In the years that followed, new surveys and deeper observations would begin to map this cosmic web in greater detail. But even in those early days, there was a growing sense that the universe had a kind of architecture, one that went beyond individual stars and even beyond individual galaxies. There is also a quieter, more human side to this story. Imagine being an astronomer in the early 1900s, reading the first reports that Andromeda and other nebulae are separate galaxies. The sky you have known all your life, the sky you may have memorized in detail, has suddenly changed its meaning. The constellations are still there. The Milky Way still glows across the darkness. But behind all of that, there is now a much deeper backdrop, filled with countless other systems you can barely see, even with the best instruments available. It is the kind of realization that can make you feel very small, but also very curious. And perhaps that is why this moment continues to resonate. It represents a turning point, not just in astronomy, but in how we think about knowledge itself. It shows how a few careful measurements and a willingness to question long-held assumptions can transform our understanding of the entire universe. It is enough to rest with that first great realization, the understanding that the Milky Way is not alone, that the universe is not a single system, but a vast collection of them. The sky above you, which may look quiet and still, is layered with these distant islands of stars, each one moving through space, each one carrying its own history written in light. If you take a moment to picture what most people imagine when they hear the word galaxy, chances are the image that forms in your mind is a spiral, a bright glowing centre, arms curling outward in a wide, elegant sweep, like a slow-motion pinwheel made of stars and light. There is something about that shape that feels both dynamic and calm at the same time, as if motion itself has settled into a steady, unhurried rhythm. Spiral galaxies have become in many ways the visual symbol of the universe beyond our own sky. They appear on book covers, posters, and screensavers, They show up in documentaries and museum exhibits as the classic portrait of a galaxy. And while they are only one of several major types, their structure and behaviour offer a particularly gentle way to understand how galaxies live and change over time. At their core, spiral galaxies are systems in motion. Everything in them is moving. Stars orbit the centre, gas drifts along the arms, dust clouds slowly collapse and give birth to new suns. Yet, when you look at a photograph of a spiral galaxy, all of that activity is frozen into a single, quiet moment, like a long exposure of a turning wheel. Our own Milky Way belongs to this family. It is a barred spiral galaxy, which means it has a central bar-shaped structure of stars running through its core, with spiral arms extending outward from the ends of that bar. From our position inside it, we cannot see its full shape directly, but through radio observations and careful mapping, astronomers have built a fairly detailed picture of its structure. When you imagine the Milky Way from the outside, it looks like a flattened disk, tens of thousands of light years across, with a bulging centre and several major arms curving around it. These arms are not solid structures. They are more like patterns, regions where stars and gas tend to bunch up as they orbit the centre. This idea can feel a bit strange at first. If the arms are not fixed objects, then what are they? The answer lies in something called density waves. As stars and gas move around the centre of a galaxy, they do not all travel at the same speed. Material closer to the centre tends to orbit faster than material farther out, much like the inner lanes of a racetrack move more quickly than the outer ones. If the arms were made of the same stars and gas staying together, they would quickly wind up tightly and lose their shape. But that is not what we see. Instead, the spiral pattern is thought to be a wave of higher density moving through the disk. As gas clouds enter this region, they get compressed, which can trigger the formation of new stars. Those stars then continue on their own paths, drifting out of the arm region over time, while new gas moves in behind them. The arm itself remains as a kind of ongoing traffic jam in the flow of material around the galaxy. This is why spiral arms often appear bright and blue in photographs. They're filled with young, hot stars that have recently formed. These stars burn their fuel quickly and do not live very long on cosmic timescales. By the time they move away from the arm region, many of them have already ended their lives in supernova explosions, enriching the surrounding space with heavier elements. Between the arms, the light is often dominated by older, redder stars. These stars can live for billions of years and form a kind of background population throughout the disk. At the very centre of most spiral galaxies lies something even more intriguing. Nearly all large galaxies, including our own, are believed to host a supermassive black hole at their core. These objects have masses millions or billions of times greater than that of the Sun. Despite their name, they do not necessarily swallow everything around them. Most of the time, they sit relatively quietly, exerting their influence through gravity rather than dramatic displays. However, when gas and dust fall toward a supermassive black hole, they can form a glowing disk of material that heats up as it spirals inward. This can cause the centre of the galaxy to shine brightly across many wavelengths of light, from radio waves to X-rays. In some galaxies, this activity becomes so intense that the core outshines the combined light of all the stars in the galaxy. In the Milky Way, the central black hole, known as Sagittarius A, is relatively calm. It is massive, but it is not currently consuming large amounts of material. As a result, our galaxy's centre does not blaze with the same intensity seen in some other spiral galaxies. Spiral galaxies come in a wide range of sizes and appearances. Some are grand and symmetrical, with 2 or 3 well-defined arms that sweep out in broad, graceful curves. Others have many arms, branching and reconnecting in complex patterns. Some have tightly wound arms that hug the centre closely. Others have arms that spread out loosely, giving the galaxy a more open look. These differences are not just cosmetic, they reflect variations in mass, rotation speed, gas content, and the galaxy's interaction history with its surroundings. One of the most famous spiral galaxies outside our own is the Andromeda Galaxy, also known as M31. It is the nearest large spiral galaxy to the Milky Way and is on a slow collision course with us. Andromeda is slightly larger and more massive than our galaxy, and it has its own system of satellite galaxies orbiting around it. When you look at images of Andromeda, you can see its disk tilted relative to our line of sight, revealing both its spiral structure and its bright central bulge. Dust lanes trace out the arms, appearing as dark streaks against the glow of stars. These dust lanes are regions where cold gas and dust block the light behind them, and they are often the sites of active star formation. Observations of Andromeda and other nearby spirals have helped astronomers understand how these galaxies are put together. By measuring the speeds at which stars and gas orbit at different distances from the centre, scientists can infer how mass is distributed throughout the galaxy. This is where one of the most important and mysterious aspects of modern astronomy comes into play. When these rotation curves are plotted, they do not behave as expected based on the visible matter alone. Stars far from the centre of a galaxy often move faster than they should, if only the gravity of the visible stars and gas were holding them in orbit. The most straightforward explanation is that there is additional mass present that we cannot see. This invisible component is called dark matter. It does not emit, absorb, or reflect light, but it exerts gravity. In spiral galaxies, dark matter is thought to form a large, roughly spherical halo that extends far beyond the visible disk. Without this halo, many galaxies would not be able to hold themselves together. The outer stars would simply drift away into space, so even though we cannot see it directly, dark matter plays a crucial role in shaping the slow, graceful turns of spiral galaxies. The process of forming a spiral galaxy is still an area of active research, but the broad outline goes something like this. In the early universe, small fluctuations in the distribution of matter grew under the influence of gravity. Regions with slightly more mass pulled in more material, becoming denser over time. Dark matter, being the dominant form of mass on large scales, clumped first, forming the basic framework. Ordinary matter, made of atoms, fell into these dark matter wells, cooling and settling into rotating disks. As this gas cooled, it formed stars, and over time a spiral structure emerged. This process did not happen in isolation. Galaxies formed in environments where interactions were common. Smaller galaxies merged to form larger ones. Close encounters could distort shapes, trigger bursts of star formation, or even transform spiral galaxies into other types. Despite these disturbances, many spirals managed to maintain their basic form for billions of years. Their disks rotate steadily, their arms continue to form new stars, and their overall structure persists through cosmic time. One of the most striking things about spiral galaxies is how much of their story is written in light that we cannot see with our eyes. Radio telescopes reveal vast clouds of hydrogen gas extending beyond the visible disk. Infrared observations show regions of warm dust where stars are forming behind thick veils. X-ray telescopes detect hot gas in the halo and energetic events near the centre. When all of these views are combined, a spiral galaxy becomes less like a simple picture and more like a layered dynamic system, with different components interacting across a wide range of scales. Closer to home, within the Milky Way, this structure shapes our own cosmic neighbourhood. Our Sun orbits the centre of the galaxy at a distance of about 27,000 light-years, taking roughly 230 million years to complete one full circuit. This period is sometimes called a galactic year. During that time, the solar system moves in and out of spiral arms, passing through regions with higher densities of gas and stars. Some researchers have even explored whether these passages might be linked to changes in Earth's environment over very long timescales, though this remains an area of ongoing study rather than a settled conclusion. From our position within the disk, the spiral structure of the Milky Way is not obvious. We see the galaxy edge on, as a band of light stretching across the sky. Dust clouds within the disk block our view of distant stars, creating dark patches and rifts in the Milky Way's glow. By using radio waves, which can pass through dust, astronomers have been able to map the distribution of hydrogen gas and trace out the spiral arms more clearly. This has revealed that the Milky Way likely has several major arms and a few smaller ones, all winding around the central bar. In other spiral galaxies, viewed from the outside, these arms can appear almost like works of art. Some show clear, sweeping curves. Others display flocculent patterns with many short, patchy arms rather than a few long ones. These differences reflect variations in how density waves move through the disk and how gas responds to them. The slow, graceful turns of spiral galaxies are measured in millions and billions of years. From one moment to the next, nothing seems to change. But over cosmic time, these rotations shape everything. They mix the contents of the galaxy, distribute heavy elements created in stars, and influence where new stars can form. This slow pace is part of what gives spiral galaxies their calm appearance. Even when dramatic events occur, like supernova explosions or the birth of massive star clusters, they are tiny flashes against the backdrop of a structure that is tens of thousands of light years across and billions of years old. There is also something quietly reassuring about the regularity of these motions. Stars orbit the centre. Gas follows along. The pattern persists. It is a kind of cosmic continuity, a steady process that carries on regardless of what happens on smaller scales. At the same time, spiral galaxies are not immune to change. Over long periods, interactions with other galaxies can alter their structure. A close pass can pull out long streams of stars, forming tidal tails that stretch far into space. A full merger can disrupt the disk entirely, often transforming a spiral into a more rounded elliptical galaxy. This means that the spiral shape, as familiar as it is, may be a phase rather than a permanent state. Galaxies can move through different forms over their lifetimes, shaped by their environment and their history of encounters. In the broader population of galaxies, spirals are common, especially in less crowded regions of the universe. In dense galaxy clusters, where interactions are frequent and the space between galaxies is relatively small, elliptical and irregular galaxies tend to dominate. Spirals are more often found in quieter neighbourhoods, where they can maintain their disks without being constantly disturbed. This distribution hints at the role of environment in shaping galaxies. A spiral galaxy in isolation can evolve slowly and steadily. One in a crowded cluster may be jostled, stripped of gas, or merged into a larger system. As telescopes look deeper into the universe, they also look further back in time. Observations of very distant galaxies show that well-formed spiral structures were less common in the early universe. Young galaxies often appear more chaotic, with clumps of star formation and irregular shapes. Over billions of years, as these systems settle and interact, the graceful spiral patterns we see today emerge. This adds a temporal dimension to the story of spiral galaxies. They are not just structures in space, they are stages in a long process of cosmic evolution. When you combine all of this, a spiral galaxy becomes more than just a pretty picture. It becomes a record of motion, matter, and time. Its shape reflects how mass is distributed. Its arms trace the flow of gas and the birth of stars. Its rotation curve reveals the presence of dark matter. Its interactions with neighbours tell a story of past encounters and future possibilities. And yet, despite all this complexity, the overall impression remains one of calm, steady turning. If you imagine drifting far enough away from a spiral galaxy to see it as a whole, you might picture it as a slow, luminous wheel turning silently in the dark. Each rotation takes hundreds of millions of years. Each arm carries countless stars along its path. Each star, in turn, may host its own system of planets, its own local rhythms of day and night. It is a layered kind of motion. Small cycles nested inside larger ones. Planets orbit stars. Stars orbit the galactic centre. Galaxies drift through space, influenced by the gravity of other galaxies, and the expansion of the universe itself. This nesting of movements is part of what makes the universe feel both intricate and cohesive. The same basic force, gravity, shapes structures on every scale, from the fall of an apple to the rotation of a galaxy. For now, though, it can be enough to hold the image of a spiral galaxy turning slowly through the dark, its arms tracing out a pattern that is both stable and dynamic, both ancient and ongoing. Somewhere within one of those arms, on a small, unremarkable star, a planet circles quietly, carrying a listener who is thinking about galaxies while the rest of the world grows a little quieter. Unlike the familiar swirl of a spiral galaxy, where arms trace out a sense of motion even in a still image, elliptical galaxies often appear calm in a different way. They do not advertise rotation with sweeping curves or bright lanes of dust. Instead, they present themselves as soft, rounded shapes, glowing gently, like distant embers suspended in the dark. Their light is smooth, their edges fade gradually into space, and their overall appearance can feel almost timeless. If spiral galaxies suggest movement and ongoing activity, elliptical galaxies tend to suggest age and quiet. They're often described as some of the oldest large structures in the universe, places where most of the dramatic phases of star formation happened long ago. What remains is a vast population of stars that have been shining for billions of years, orbiting in patterns that are less orderly and more subtle than the rotating disks of spirals. At first glance, an elliptical galaxy can seem simple. It might look like a glowing oval or a nearly perfect sphere, without much detail to draw the eye. But that simplicity is deceptive. Beneath that smooth light lies a complex history of motion, interaction, and transformation. The name elliptical comes from their general shape. Some are nearly round, classified as E0, meaning they look almost like spheres. Others are more stretched out, appearing as elongated ovals. The most flattened might be labelled E7, though even these are not flat in the same way a spiral disk is. Instead of being thin and layered, elliptical galaxies are more like three-dimensional clouds of stars, with stars moving in many different directions. This difference in motion is one of the key features that sets ellipticals apart. In a spiral galaxy, most stars follow roughly circular orbits around the centre, all moving in the same general direction. In an elliptical galaxy, stars travel along a wide variety of paths. Some move in elongated orbits that take them far from the centre and then back again. Others move in more circular patterns. The overall result is a kind of stellar swarm, where motion is distributed in many directions rather than organised into a single rotating plane. This gives elliptical galaxies a sense of stillness when viewed from afar. There is motion, of course, but it does not present itself as a clear, large-scale rotation that we can easily trace. Elliptical galaxies come in a wide range of sizes. Some are small, containing just a few million or a few 100 million stars. These are called dwarf ellipticals. Others are among the largest galaxies in the universe. The biggest of them, known as giant ellipticals or CD galaxies, can contain trillions of stars and stretch across millions of light years. These giants are often found at the centres of galaxy clusters, where gravity has drawn many galaxies together over cosmic time. In these crowded environments, elliptical galaxies tend to dominate. This is not a coincidence. The very process that brings galaxies into close proximity also tends to favour the formation of ellipticals. When galaxies interact, especially when they collide and merge, their structures can be dramatically altered. Two spiral galaxies coming together will not simply pass through each other like ghosts. Their gravitational fields interact, pulling stars and gas into long arcing streams. The delicate disks can be disrupted, twisted, and eventually erased. Over time, the merged system can settle into a more rounded, elliptical shape. This is one of the leading ideas about how many large elliptical galaxies form. Rather than being born as smooth, featureless systems, they are thought to be the end products of multiple mergers, layered on top of one another over billions of years. Each merger adds stars, redistributes motion, and often triggers bursts of star formation. But as these bursts fade and the gas needed to form new stars is used up or blown away, the galaxy enters a quieter phase. Star formation slows or stops, leaving behind a population dominated by older, longer-lived stars. This is why elliptical galaxies often appear redder than spirals. The bright blue stars that dominate spiral arms are short-lived. They burn hot and fast, and they do not last long on cosmic timescales. In elliptical galaxies, most of those young hot stars are gone. What remains are older, cooler stars that shine with a softer, redder light. This colour difference is more than just a visual detail. It is a clue to the galaxy's history. It tells a story of a system that formed many of its stars early on and has since settled into a long, slow phase of aging. If you could somehow rewind time and watch a large elliptical galaxy form, you might see a chaotic scene. Smaller galaxies would approach, drawn together by gravity. As they interact, their shapes would distort. Gas clouds would collide and compress, triggering intense waves of star formation. Supernova explosions would light up the surrounding space, scattering heavy elements and heating the gas. Over time, as more and more mergers take place, the system would grow larger and more massive. The individual disks and structures of the original galaxies would be lost in the mixing process. Eventually, what remains is a single, large, rounded galaxy, with stars moving in a wide range of orbits and little gas left to fuel new stars. This process does not happen quickly. It unfolds over billions of years. From a human perspective, it is so slow that it might as well be still. At the centres of most large elliptical galaxies, as in spirals, there are supermassive black holes. In fact, the most massive black holes known are often found in the largest elliptical galaxies. The mass of the central black hole appears to be related to the mass of the galaxy's central bulge, suggesting a deep connection between the growth of galaxies and the growth of their black holes. In the early, more active phases of an elliptical galaxy's life, when gas is abundant and mergers are common, these central black holes can be very active. They can consume large amounts of material, forming bright, energetic regions known as active galactic nuclei. The energy released can heat, or even expel gas from the galaxy, further reducing the potential for new star formation. This feedback process may help explain why many elliptical galaxies end up so quiet. The very mechanisms that drive their growth and early activity can also contribute to shutting down the conditions needed for continued starbirth. When astronomers observe elliptical galaxies in different wavelengths of light, they uncover layers of complexity that are not obvious in simple optical images. X-ray observations often reveal large halos of hot gas surrounding these galaxies, especially in cluster environments. This gas can be heated by the combined effects of supernova explosions, galaxy interactions, and energy output from central black holes. Radio observations can show faint jets or lobes of material being ejected from the cores of some ellipticals, evidence of past or ongoing activity around their central black holes. All of this adds to the picture of elliptical galaxies as systems that may look calm on the surface, but have experienced dramatic events in their past. One of the most interesting roles elliptical galaxies play is as markers of large-scale structure in the universe. The biggest ellipticals often sit at the centres of galaxy clusters, acting as gravitational anchors. These clusters can contain hundreds or even thousands of galaxies, along with vast amounts of dark matter and hot gas. The central elliptical galaxy in a cluster is sometimes referred to as a brightest cluster galaxy, or BCG. These galaxies can grow to enormous sizes by gradually absorbing smaller galaxies that pass too close. Over time, this process can create a galaxy that is far larger and more massive than most others. From a distance, a cluster of galaxies can look like a swarm of lights, with a particularly bright and dominant glow at the centre. That central glow often comes from one of these giant elliptical galaxies. This central position gives elliptical galaxies a kind of quiet authority in the cosmic landscape. They sit at the intersections of the cosmic web, where filaments of galaxies and dark matter meet. They are not just individual systems, they are part of much larger structures that span millions of light years. Despite their reputation for stillness, elliptical galaxies are not completely inactive. They can still contain small amounts of gas and dust. They can still experience minor mergers with smaller galaxies, and in some cases they can even form new stars, though at a much lower rate than spirals. In recent years, observations have revealed that some elliptical galaxies show signs of cold gas in their centres, possibly falling in from their surroundings or left over from past interactions. This gas can sometimes trigger limited star formation, adding a small population of younger stars to an otherwise old system. This reminds us that even the most ancient-looking galaxies are not truly frozen in time. They continue to evolve, just on slower and subtler paths. There is also a category of galaxies that sits somewhere between spirals and ellipticals, often called lenticular galaxies. These have a disc-like structure but lack the prominent spiral arms and active star formation of true spirals. They are sometimes thought of as spirals that have lost their gas, possibly through interactions with other galaxies or the hot gas in clusters. Lenticular galaxies add another layer to the idea that galaxy types are not fixed identities, but stages in a longer evolutionary process. When astronomers look at very distant galaxies, they are looking back in time to when the universe was much younger. In those early epochs, fully formed elliptical galaxies are less common. Instead, galaxies often appear smaller, more irregular, and more actively forming stars. This supports the idea that many of today's large ellipticals are the products of a long history of mergers and growth. They are not primordial structures that formed fully grown. They are built up piece by piece, interaction by interaction. The age of the stars within elliptical galaxies also tells a story. By analysing the light from these stars, astronomers can estimate when they formed. In many large ellipticals, a significant fraction of the stars appear to have formed relatively early in the universe's history, within the first few billion years after the Big Bang. This suggests that these galaxies went through intense periods of star formation early on, followed by a long decline. Their present-day calm is the result of a very active youth. If spiral galaxies feel like ongoing projects, with new stars constantly being added and structures maintained through steady rotation, elliptical galaxies feel more like completed works. Most of their building happened long ago. What remains is a system slowly aging, its stars evolving and fading over immense spans of time. There is something quietly contemplative about that idea. These galaxies carry within them the record of some of the earliest major episodes of structure formation in the universe. They are like archives, preserving the outcomes of processes that shaped the cosmos when it was still relatively young. At the same time, their role in galaxy clusters means they are still part of an ongoing story. As clusters grow and change as new galaxies fall in along cosmic filaments, the central ellipticals continue to accumulate mass and influence. From a visual perspective, elliptical galaxies can be subtle and understated. They do not always make for dramatic images in the way spirals do, with their bright arms and dark dust lanes. But their simplicity has its own kind of presence. A large elliptical galaxy can appear as a smooth, glowing shape, fading gently into the background of space like a quiet light in a vast room. If you imagine drifting near one, you might picture a sky filled with stars in every direction, without the clear band of a disk or the pattern of arms. The view would be more evenly spread, a kind of star field that surrounds you rather than lying in a plane. The motion of those stars would be complex, with orbits crossing and weaving through one another in 3 dimensions. Over time, this mixing helps maintain the smooth, rounded appearance of the galaxy. This kind of structure is often described as being in a state of dynamic equilibrium. The galaxy is not static. Stars are moving. Gravity is constantly at work, but the overall shape remains relatively stable over long periods. That balance between motion and stability is part of what gives elliptical galaxies their sense of stillness. In the broader picture of the universe, elliptical galaxies represent one of the main outcomes of cosmic evolution. They show what can happen when gravity, time, and interaction combine over billions of years. They are reminders that the universe is not just a place of constant creation, but also of long-term transformation and aging. As this journey continues, it becomes clear that no single galaxy type tells the whole story. Spirals, ellipticals, irregulars, and dwarfs each capture different aspects of how matter organizes itself on the larger scales. Elliptical galaxies, with their ancient stars and smooth forms, highlight the role of mergers and environment. They show how violent beginnings can lead to quiet endings, at least in relative terms. Sometimes the universe refuses to follow neat categories. After the smooth glow of elliptical galaxies and the sweeping curves of spirals, there are galaxies that seem to shrug at the very idea of order. They do not form tidy disks. They do not settle into rounded, symmetrical shapes. Instead, they appear scattered, stretched, clumpy, or lopsided, as if someone took a handful of stars and gas and let them fall into space without bothering to arrange them afterward. These are the galaxies we call irregular, not because they are flawed, but because they do not fit comfortably into the patterns we use to describe most others. At first glance, an irregular galaxy can look like a mistake, a patch of light with no clear centre, a jumble of bright and dark regions, a shape that seems unfinished. But when you spend a little time with them, they start to feel less like accidents and more like records. Each one carries visible evidence of forces that have acted on it, of interactions, pressures, and histories written directly into its structure. The term irregular is a broad one. It does not describe a single, well-defined type of galaxy. Instead, it gathers together a wide variety of systems that share one main feature. They lack the clear, ordered shape of a spiral or an elliptical. Beyond that, they can be very different from one another in size, mass, brightness, and behaviour. Some irregular galaxies are small and faint, with just a few million stars. Others are surprisingly active, forming new stars at a rapid pace. Some appear isolated, drifting through space with no obvious neighbours. Others are clearly being pulled apart or reshaped by nearby galaxies. In many cases, irregular galaxies are the results of interaction. Gravity is a powerful sculptor on cosmic scales. When galaxies pass close to one another, their shapes can be distorted. Spiral arms can be stretched into long streams. Gas can be pulled out into space. Entire sections of a galaxy can be displaced or rearranged. If the encounter is gentle, the galaxy might recover over time, settling back into a more regular form. If it is more severe, the result can be a long-lasting irregular shape, a kind of frozen moment in a slow-motion cosmic collision. One of the most famous examples of an irregular galaxy is the Large Magellanic Cloud. This is a small galaxy that orbits the Milky Way, visible to the naked eye from the southern hemisphere as a hazy patch of light. It does not have the well-defined disk of a spiral or the smooth glow of an elliptical. Instead, it appears as a loose, uneven collection of stars and gas, with bright regions where new stars are forming. The Large Magellanic Cloud, along with its smaller companion, the Small Magellanic Cloud, is interacting gravitationally with the Milky Way. This interaction has stretched out long streams of gas and stars known as the Magellanic Stream that trail behind them across the sky. These streams are a clear sign that these small galaxies are being shaped by their larger neighbour. Over time, they may be gradually pulled apart and absorbed, their stars becoming part of the Milky Way's extended halo. In this way, irregular galaxies can be seen as transitional systems. They may be in the process of becoming something else. A small irregular galaxy might eventually be merged into a larger one. A distorted spiral might slowly relax into a more elliptical form after a major interaction. This makes irregular galaxies especially interesting to astronomers, because they offer a kind of snapshot of change in progress. While spiral and elliptical galaxies often look stable on the surface, irregulars tend to show the signs of recent or ongoing events more clearly. Another well-known irregular galaxy is Messier 82, often called the Cigar Galaxy. It lies close to a larger spiral galaxy, Messier 81, and the two have interacted in the past. That interaction has triggered intense star formation in Messier 82, making it a starburst galaxy. In images, Messier 82 looks chaotic. Bright clusters of young stars crowd its centre. Streams of gas and dust are being blown out of the galaxy by the combined effects of stellar winds and supernova explosions. These outflows form towering plumes of glowing material that extend far above and below the main body of the galaxy. Here, the irregular shape is tied directly to activity. The galaxy is not just a quiet collection of stars, it is a place where energy is being released on a massive scale, reshaping its structure in real time, at least on cosmic timescales. Irregular galaxies are also common in the early universe. When astronomers look at very distant galaxies, they often see systems that look clumpy and disorganized. These young galaxies are still forming. Gas is collapsing into stars, small structures emerging to form larger ones. The neat categories of spiral and elliptical have not yet had time to fully emerge. In that sense, irregular galaxies can be seen as echoes of the universe's youth. They show what galaxies might have looked like before they settled into more stable forms. Some irregular galaxies are classified as dwarf irregulars. These are small, low-mass systems that contain relatively few stars compared to larger galaxies. They often have high amounts of gas relative to their size, which allows them to continue forming new stars over long periods. Because of their small size, dwarf irregulars are especially sensitive to their environment. A close pass by a larger galaxy can easily disturb them. Gas can be stripped away. Their shapes can be stretched or compressed. At the same time, because they are simpler systems, they can be useful for studying basic processes of star formation and chemical evolution. In a large spiral or elliptical galaxy, many generations of stars and many layers of history are mixed together. In a small dwarf irregular, the story can be easier to untangle. These galaxies often have low levels of heavy elements, which suggests that they have not gone through as many cycles of star formation and supernova enrichment as larger galaxies. This makes them, in a way, more chemically primitive, offering a glimpse into conditions that may have been common in the early universe. When you look at images of irregular galaxies, one of the first things you might notice is how patchy they are. Bright knots of light mark regions where new stars are forming. Darker areas show where dust clouds block the light. The overall shape can seem lopsided, with most of the brightness concentrated on one side or in a few scattered regions. This patchiness reflects the uneven distribution of gas. In a spiral galaxy, gas is often organized into arms, creating a more regular pattern of star formation. In an irregular galaxy, gas can be clumped in unpredictable ways, leading to bursts of star formation in specific areas while other regions remain relatively quiet. This can give irregular galaxies a sense of immediacy. They often look active, as if something is happening right now, rather than long ago. Bright blue stars, glowing nebulae, and strong emission from ionized gas all point to recent and ongoing starbirth. At the same time, irregular galaxies can also contain older stars. Their histories are not limited to their most recent activity. They too have been around for billions of years, experiencing cycles of growth, interaction, and change. The difference is that their smaller size and looser structure make those changes more visible. One way to think about galaxy shapes is to imagine gravity as a kind of organizing force. In a large, massive galaxy, gravity is strong and can pull stars and gas into a more orderly arrangement. In smaller galaxies, gravity is weaker, and external influences can have a greater impact. This is one reason why irregular galaxies are often small. Their lower mass makes it harder for them to maintain a stable, regular structure in a universe where interactions and tidal forces are common. But irregularity is not always a sign of weakness or transience. Some irregular galaxies are relatively massive and have maintained their shapes for long periods. Their irregularity can be an inherent feature of how they formed, rather than just the result of recent disruption. There is also a class of galaxies known as peculiar galaxies. These are systems that show unusual features that do not fit neatly into standard categories. They might have rings, tails, multiple cores, or other strange structures. Many of these peculiarities are the result of interactions or mergers, but some may reflect more complex internal processes. In images, peculiar and irregular galaxies often stand out. They look like the exceptions, the ones that break the rules. But in doing so, they highlight the fact that the universe is not a simple place. The tidy diagrams and classification schemes are tools we use to organize our understanding, not rigid boundaries that the cosmos must obey. From a broader perspective, irregular galaxies play an important role in the overall population of galaxies. They're common, especially at smaller sizes. They contribute to the ongoing growth of larger galaxies through mergers and accretion. They act as laboratories for studying star formation in less structured environments. They also remind us that galaxies are not isolated, unchanging objects. They are shaped by their surroundings. They respond to the gravitational pull of neighbours. They evolve as they move through the cosmic web. The cosmic web itself is a vast network of filaments and nodes made mostly of dark matter, with galaxies tracing out its structure. Along these filaments, galaxies and gas flow toward denser regions, such as clusters. As they travel, they can interact with other galaxies and with the hot gas that filled cluster environments. For a small irregular galaxy, passing through such a region can be a transformative experience. Gas can be stripped away by pressure from the hot intracluster medium, a process known as RAM pressure stripping. Without its gas, the galaxy loses the ability to form new stars and may eventually fade into a more passive system. Tidal forces can stretch a galaxy into long streams of stars which can wrap around larger galaxies or trail behind them like ribbons. These streams are not just visually striking, they provide valuable information about the distribution of dark matter and the history of galaxy interactions. In this way, irregular galaxies contribute to the larger story of how structure forms and changes in the universe. They are both actors and evidence, both participants in and records of cosmic processes. There is also something conceptually appealing about irregular galaxies. They stand as a counterpoint to the idea that nature always favours symmetry and order. While symmetry does appear in many places, from the shapes of snowflakes to the structure of spiral arms, there is also a great deal of variation and complexity. Irregular galaxies embody that complexity on a grand scale. They show that even when the same basic laws of physics apply everywhere, the outcomes can be diverse. From a distance, a spiral galaxy might look like a carefully drawn pattern. An irregular galaxy looks more like a sketch in progress, with lines crossing, fading, and reappearing in unexpected places. If you imagine drifting near an irregular galaxy, the view might feel less predictable. Instead of a clear band of stars in a disk or a smooth surrounding glow, you might see clusters and gaps, bright regions and dark voids, all mixed together in a more uneven way. The sky within such a galaxy could change more dramatically as you move from one region to another. One area might be filled with young, bright stars and glowing clouds of gas. Another might be quieter, dominated by older stars and little ongoing activity. This unevenness can make irregular galaxies feel more like landscapes than like single, unified structures. They have regions with different characters, different histories, and different futures. In the context of the universe as a whole, this diversity is part of what makes the study of galaxies so rich. If every galaxy looked and behaved the same, there would be less to learn from comparing them. The differences, the outliers, the messy cases often provide the strongest clues about the underlying processes at work. Irregular galaxies also highlight the role of chance in cosmic evolution. The exact path a galaxy takes through space, the neighbours it encounters, the timing and angle of interactions, all of these can influence its shape and development. Two galaxies that start out similar can end up very different depending on what happens to them over billions of years. This sense of contingency adds another layer to the story of the universe. It is not just a machine running through a fixed program. It is a dynamic system where small differences can lead to varied outcomes. As observations continue to improve, astronomers are finding irregular and peculiar galaxies in greater detail and at greater distances. Deep surveys reveal galaxies with shapes that challenge existing categories, suggesting that our classification systems may need to evolve as we see more of the universe. Some of these distant early galaxies look like collections of bright clumps connected by faint bridges of light. Others appear as elongated streaks or partial rings. These forms may represent stages in galaxy formation that are rare or absent in the nearby universe. By studying these systems, scientists can test models of how galaxies assemble from smaller pieces and how they respond to their environment over time. All of this reinforces the idea that irregular galaxies are not just oddities at the edge of the classification chart. They are an essential part of the cosmic population, representing both the beginnings and the disruptions of galactic life. There is a certain kind of quiet beauty in that messiness. It is not the beauty of symmetry or smoothness, but the beauty of process. It is the beauty of something shaped by forces acting over immense spans of time, leaving behind marks that can still be read. When you look at an image of an irregular galaxy, you're not just seeing a collection of stars, you're seeing the imprint of gravity, motion, and interaction. You're seeing a record of encounters that may have happened hundreds of millions or billions of years ago. In that sense, every irregular shape is a kind of story. A stretched arm might mark a close pass with a neighbour. A bright cluster of stars might point to a recent compression of gas. A faint stream of light might be the remains of a smaller galaxy being slowly absorbed. Somewhere in the vast expanse of space, a patch of stars and gas drifts along, pulled and pushed by forces far larger than itself, forming and reforming as time passes. Its outline is uneven, its structure is complex, its history is written in light and shadow. While the grand spirals and massive ellipticals tend to capture most of the attention, there is a quieter population of galaxies that far outnumbers them. These are the dwarf galaxies, small in size, modest in brightness, and often easy to overlook, yet deeply woven into the story of how the universe builds its largest structures. If the biggest galaxies are like cities of stars, dwarf galaxies are more like small towns and villages, scattered everywhere, shaping and being shaped by their surroundings over immense stretches of time. At first glance, a dwarf galaxy might not seem especially impressive. Some contain only a few million stars, compared to the hundreds of billions found in a large spiral like the Milky Way. They can be faint, diffuse, and hard to spot against the background of space. Yet, in terms of sheer numbers, they are the most common type of galaxy in the universe. Wherever a large galaxy exists, it is usually surrounded by a collection of these smaller companions, orbiting, drifting, and sometimes slowly disappearing into their larger neighbour. Our own galaxy is no exception. The Milky Way is encircled by dozens of known dwarf galaxies, and likely many more that are too faint to have been detected so far. Some of the most familiar are the large and small Magellanic Clouds, visible to the naked eye from the southern hemisphere. Others, like the Sagittarius dwarf spheroidal galaxy, are so faint and spread out that they were only discovered in the late 20th century, even though they passed through the Milky Way's halo. These small galaxies come in several different forms. Some are dwarf irregulars, with patchy shapes and ongoing star formation. Others are dwarf ellipticals or dwarf spheroidals, which are smoother, rounder, and largely inactive in terms of new star birth. There are also transitional types that sit somewhere in between, hinting at the idea that these categories are not fixed identities, but stages in a longer evolutionary path. One of the most interesting things about dwarf galaxies is how strongly their lives are influenced by their environment. Because they are small and have relatively weak gravity, they are especially vulnerable to the pull of larger galaxies and the conditions of the space they move through. When a dwarf galaxy orbits a massive spiral or elliptical, it can experience tidal forces that stretch and distort it. Over time, these forces can pull stars away, creating long, faint streams that wrap around the larger galaxy. These stellar streams are like footprints, tracing the path the dwarf has taken and revealing the shape of the invisible dark matter halo that surrounds the larger system. The Sagittarius dwarf galaxy provides a clear example of this process. It is currently being torn apart by the Milky Way's gravity. Its stars are being stripped away and spread out into a vast looping stream that encircles our galaxy. In a sense, this dwarf galaxy is in the process of becoming part of the Milky Way, its identity slowly dissolving into a larger whole. This kind of interaction is not rare. Over the history of the universe, large galaxies are thought to have grown, at least in part, by absorbing many smaller ones. Each merger adds stars, gas, and dark matter to the larger system. Dwarf galaxies, then, are not just companions, they are building blocks. This idea fits well with a broader picture of how structure forms in the universe. In the early cosmos, matter was not evenly distributed. Small clumps formed first, pulled together by gravity. Over time, these small structures merged to form larger ones, which in turn merged to form even larger systems. Galaxies grew hierarchically, from the bottom up. In this view, today's dwarf galaxies can be seen as survivors of that early era, systems that either have not yet been absorbed or that exist in regions where interactions are less frequent. They are like living fossils, preserving conditions that were more common when the universe was young. Many dwarf galaxies have low levels of heavy elements. In astronomy, anything heavier than hydrogen and helium is considered a heavy element, or metal. These elements are created in stars and spread into space through stellar winds and supernova explosions. A galaxy that has gone through many generations of star formation will have a higher metal content. A galaxy with fewer cycles of star birth and death will remain more chemically simple. The low metal content of many dwarf galaxies suggests that they have had relatively quiet histories. They have formed stars, but not at the same intense rate seen in larger galaxies. This makes them valuable laboratories for studying star formation under more primitive conditions, similar to those that may have existed in the early universe. At the same time, some dwarf galaxies are surprisingly active. Dwarf irregulars, in particular, can host bright regions of star formation. Because their gravitational pull is weaker, the energy released by supernova explosions and stellar winds can have a dramatic effect. It can blow gas out of the galaxy entirely, temporarily halting star formation. Later, gas from the surrounding space may fall back in, starting the process again. This cycle of activity and quiescence can repeat many times over a galaxy's lifetime, giving dwarf galaxies a kind of stop-and-start rhythm. In larger galaxies, the effects of individual supernovae are more localized. In a dwarf galaxy, a single cluster of massive stars can influence the structure of the entire system. This makes dwarfs especially sensitive to the details of stellar feedback, the way energy from stars shapes the surrounding gas. Because of this sensitivity, dwarf galaxies have become important in testing models of galaxy formation and evolution. By comparing observations with simulations, astronomers can see how well their theories reproduce the properties of these small systems. Another reason dwarf galaxies are so interesting is their relationship with dark matter. Observations suggest that dwarf galaxies are dominated by dark matter even more strongly than larger galaxies. In many cases, the mass of dark matter far exceeds the mass of visible stars and gas. This makes dwarf galaxies excellent targets for studying the nature and distribution of dark matter. By measuring how stars move within these galaxies, astronomers can infer how much unseen mass must be present to hold them together. In some dwarf spheroidal galaxies orbiting the Milky Way, the stars move at speeds that would cause them to escape if only the visible matter were providing the gravity. The fact that they remain bound suggests that a large amount of dark matter is present. These systems are, in a sense, some of the darkest galaxies in the universe. They emit very little light compared to the mass they contain. This has even led to the idea that there may be many more dwarf galaxies out there that are almost entirely dark, containing very few stars and therefore being extremely difficult to detect. Finding and studying these faint systems is one of the challenges of modern astronomy. As surveys become more sensitive, new dwarf galaxies are still being discovered around the Milky Way and other nearby galaxies. Each new detection adds another piece to the puzzle of how many such systems exist and how they are distributed. The Large and Small Magellanic Clouds offer a closer look at what dwarf galaxies can be like. These two companions to the Milky Way are relatively massive for dwarfs and are actively forming stars. The Large Magellanic Cloud in particular contains a spectacular region known as the Tarantula Nebula, one of the most active star-forming regions in the local universe. The interaction between the Magellanic Clouds and the Milky Way has shaped all three systems. The clouds are connected by a bridge of gas. They trail behind them a long stream of material, and their motion through the Milky Way's halo may be triggering bursts of star formation within them. This kind of three-way interaction shows how even small galaxies can play significant roles in shaping larger ones. Gas stripped from a dwarf galaxy can fall into a larger galaxy, fueling new star formation. Stars from a dwarf can become part of the larger galaxy's halo, adding to its stellar population. Over time, the line between the larger and smaller systems becomes blurred. The history of a big galaxy is, in part, a record of all the smaller ones it has encountered and absorbed. Some dwarf galaxies, however, manage to avoid close encounters for long periods. Those that exist in more isolated regions can evolve more gently. They may retain their gas and continue forming stars at a slow, steady pace. Their shapes may remain irregular or loosely organised. These isolated dwarfs provide a contrast to those that live in the crowded environments near massive galaxies or in dense clusters. By comparing these different populations, astronomers can see how environment influences galaxy evolution. In galaxy clusters, dwarf galaxies can be especially vulnerable. The space between galaxies in a cluster is filled with hot, thin gas. As a dwarf galaxy moves through this medium, it can experience a kind of pressure that strips away its own gas. This process, known as ram pressure stripping, can leave the dwarf galaxy starved of the material needed to form new stars. Over time, such a galaxy may fade and become a dwarf elliptical or dwarf spheroidal, dominated by older stars and little ongoing activity. This transformation highlights the idea that dwarf galaxies are not just small versions of larger ones. They can change types over their lifetimes, influenced by where they live and what they encounter. When astronomers look at the distribution of dwarf galaxies around the Milky Way, they find that they are not randomly scattered. Many appear to lie in a kind of flattened arrangement, sometimes referred to as a plane of satellites. The significance of this pattern is still debated, but it raises interesting questions about how these dwarfs were captured and how dark matter is distributed in the Milky Way's halo. Similar patterns have been observed around other large galaxies, suggesting that the way dwarf galaxies are arranged may carry information about the formation history of their larger hosts. Dwarf galaxies also play a role in shaping the chemical evolution of the universe. Because they often have lower metal content, the stars they form can resemble the earliest generations of stars that formed after the Big Bang. By studying these stars, astronomers can gain insights into the processes that produced the first heavy elements. Some of the oldest stars in the Milky Way's halo are thought to have originated in dwarf galaxies that were later absorbed. In this way, the chemical fingerprints of those small systems are preserved within our own galaxy. This idea connects the small and the large in a very direct way. The composition of the Sun, the Earth, and even our own bodies may in part reflect the contributions of ancient dwarf galaxies that merged with the Milky Way billions of years ago. There is also a subtle beauty in the way dwarf galaxies challenge our expectations. Because they are small and faint, they can easily be missed. Yet, they hold clues to some of the biggest questions in cosmology, including the nature of dark matter and the processes that govern the early universe. In simulations of the universe based on the current understanding of dark matter, large galaxies like the Milky Way are expected to be surrounded by hundreds or even thousands of dwarf galaxies. Observationally, we see far fewer. This discrepancy is known as the missing satellites problem. There are several possible explanations. Many dwarf galaxies may be so faint that we simply have not detected them yet. Others may have formed very few stars and are therefore difficult to see. Or our models of dark matter and galaxy formation may need refinement. As new telescopes and surveys come online, including those designed to map the sky in unprecedented detail, astronomers hope to find more of these elusive systems and better understand their true numbers. Beyond their scientific importance, there is something quietly appealing about dwarf galaxies on a more human level. They are small, often overlooked, yet persistent. They drift through space for billions of years, sometimes alone, sometimes in the shadow of much larger neighbours. They can be stretched, stripped, and reshaped, but many of them continue to exist, adapting to their circumstances. Their stories are not always about growth and dominance. Sometimes they're about survival and transformation. If you imagine a night sky from within a dwarf galaxy, it might look very different from the view in a large spiral. The number of stars could be fewer, the structure might be less defined, but the same fundamental processes would still be at work. Stars would be born, stars would age and die, elements would be created and spread. The scale is smaller, but the story is still vast. In the broader tapestry of the universe, dwarf galaxies fill in the spaces between the giants. They trace out the fine structure of the cosmic web. They provide the raw material for the growth of larger systems. They preserve echoes of the early universe in their simple chemistry and ancient stars. They are in many ways the quiet majority. When you look up at the night sky, it can feel as though everything above you is fixed in place. The stars hold their patterns. The Milky Way stretches across the darkness in the same familiar way, night after night. Even when you know, intellectually, that everything is moving, the scale of that motion is so vast and so slow that it fades into the background of everyday experience. But on the larger scales, galaxies are anything but still. They drift through space, pulled along invisible paths by gravity. They gather in groups and clusters. They pass close to one another, tugging and stretching, sometimes gliding past, sometimes becoming entwined in long, complicated dances that can last for hundreds of millions of years. And every so often those dances end in collisions and mergers that reshape the galaxies involved in profound and lasting ways. The word collision might bring to mind something sudden and violent, like two cars crashing into each other. On cosmic scales, though, things happen differently. Galaxies are mostly empty space. The distance between stars is so vast that when two galaxies pass through one another, direct star-on-star collisions are extremely rare. Instead of a single dramatic impact, what happens is more like two enormous clouds of points of light and gas drifting through each other, their structures slowly distorted by mutual gravity. The real drama unfolds over time. As galaxies approach, their gravitational fields begin to interact long before their visible edges touch. Stars and gas feel the pull of the other system. Spiral arms can be stretched into long arcs. Entire sections of a galaxy can be drawn out into space, forming luminous streams known as tidal tails. These tails can extend for hundreds of thousands of light years, marking the paths the galaxies have taken and revealing the strength of the forces involved. One of the most famous examples of this process is a pair of galaxies known as the antennae galaxies. In images, they look like two bright, distorted cores connected by sweeping arcs of stars and gas that resemble the antennae of an insect. These two spiral galaxies began interacting hundreds of millions of years ago, and they are now in the midst of a slow merger. Between them, in the regions where gas clouds have been compressed by gravitational forces, new stars are forming at a rapid pace. clusters of young, bright stars light up the overlapping region, creating a kind of cosmic construction site where new structures are being built out of the material stirred up by the encounter. This is a common feature of galaxy interactions. When gas clouds are compressed, they can collapse more easily, triggering bursts of star formation. These starbursts can dramatically change the appearance of a galaxy, making it brighter and bluer for a time as hot. Young stars dominate the light. Over longer periods, though, the same processes that spark these bursts can also lead to a slowdown. As gas is used up or heated and expelled, the raw material for new stars becomes scarce. The galaxy can transition from an active star-forming phase to a quieter, more passive one. This cycle of activity and decline is one of the ways that galaxy mergers can transform spirals into ellipticals. Two disc-shaped galaxies, each with its own orderly rotation, can collide and merge into a single, more rounded system where stars move in many different directions. The spiral structure is lost, replaced by the smoother, more three-dimensional shape of an elliptical galaxy. This idea, known as the merger hypothesis, is supported by both observations and computer simulations. When scientists model the collision of two spiral galaxies on a computer, allowing gravity and gas dynamics to play out over billions of years, the result often resembles a large elliptical galaxy. The process is not quick. From the first close pass to the final settling of the merged system can take 1 billion years or more. During that time, the galaxies may swing past each other several times, each encounter pulling out more material and reshaping their forms. As the cores of the two galaxies finally come together, something else happens at the very centre. If both galaxies contain supermassive black holes, those black holes will eventually find each other and form a binary system. Over time, they spiral closer, losing energy through interactions with surrounding stars and, at the final stages, through the emission of gravitational waves. When they merge, they create a single, even more massive black hole. This event can release enormous amounts of energy and may help drive powerful outflows of gas from the centre of the newly formed galaxy. These central processes add another layer to how mergers influence galaxy evolution. They are not just rearranging stars and gas on large scales. They are also reshaping the conditions in the deepest core. Not all interactions end in full mergers. Sometimes galaxies pass by each other at a distance that is close enough to cause distortion, but not close enough to result in a permanent union. These flybys can still have significant effects. A passing galaxy can trigger spiral arms to become more pronounced. It can pull gas toward the centre, fueling star formation or black hole activity. It can leave behind tidal features that persist long after the encounter is over. In this way, even brief meetings can leave lasting marks. On a larger scale, galaxies often live in groups and clusters where such encounters are more common. In a dense cluster environment, galaxies are packed relatively close together, and the gravitational influence of the cluster as a whole can strip gas from individual galaxies as they move through the hot, thin gas that fills the space between them. This process, known as ram pressure stripping, can remove the fuel needed for star formation, gradually turning spiral galaxies into more passive systems. Over time, this can change the overall mix of galaxy types within a cluster, favouring ellipticals and lenticulars over spirals. This highlights an important idea in galaxy evolution. It is not just a galaxy's internal properties that matter, its surroundings play a crucial role. A galaxy in a quiet, isolated region of the universe may go for billions of years without a significant encounter. It can maintain its structure and continue forming stars at a steady pace. A galaxy in a crowded cluster may experience repeated interactions, gas stripping, and mergers that dramatically alter its path. The cosmic web, that vast network of filaments and nodes made primarily of dark matter, sets the stage for these differences. Galaxies flow along filaments toward denser regions, such as clusters. As they do, they are more likely to meet other galaxies and experience the forces that drive change. This flow means that the universe is not just expanding, On smaller scales, matter is also moving inward, gathering into larger and larger structures. Over cosmic time, this leads to a kind of hierarchy. Small galaxies merge to form larger ones. Groups of galaxies merge to form clusters. Clusters can come together to form superclusters. Each level of this structure has its own dynamics, but they are all connected by gravity. One of the most striking pieces of evidence for galaxy mergers comes from the stars themselves. When astronomers study the motions and chemical compositions of stars in the halos of large galaxies, they often find distinct streams and clumps that stand out from the rest of the population. These are the remains of smaller galaxies that were absorbed in the past. Their stars still carry the chemical signatures of their original homes, even after being spread out around the larger galaxy. In the Milky Way, several such streams have been identified, including the debris from the Sagittarius dwarf galaxy. These stellar fossils provide a kind of archaeological record, allowing astronomers to reconstruct the merger history of our galaxy. By comparing observations with simulations, scientists can estimate how many mergers a galaxy like the Milky Way has experienced, and how those events have shaped its structure. It turns out that even relatively calm-looking galaxies have often had eventful pasts. There is also a more subtle kind of interaction that does not involve close passes or dramatic collisions. Galaxies can influence each other through their gravitational fields over large distances. This can lead to the alignment of spins, the formation of filaments of galaxies, and the shaping of large-scale patterns in the distribution of matter. These effects are part of the reason why the universe, on its largest scales, looks like a web rather than a random scattering. When astronomers map the positions of millions of galaxies, they find that they tend to lie along long thread-like structures with vast empty regions in between. At the intersections of these filaments, galaxy clusters form, often anchored by massive elliptical galaxies at their centres. This large-scale structure is the result of billions of years of gravitational growth, starting from tiny fluctuations in the density of matter in the early universe. Galaxy collisions and mergers are the small-scale expressions of that same process. They are the local, visible manifestations of gravity's long-term work. If you imagine time-lapse footage of the universe, sped up so that billions of years pass in a few seconds, you would see galaxies moving along these filaments, approaching one another, interacting, merging, and then moving on as part of larger systems. It would look less like a static picture, and more like a slow, continuous flow. There is also a quieter side to this story. Not all changing galaxies comes from dramatic events. Even in isolation, galaxies evolve. Stars form, live, and die. Gas is converted into heavier elements. Energy is released and dissipated. Over long periods, these internal processes can alter the balance of a galaxy, changing the rate at which it forms new stars and the distribution of its material. But interactions often act as accelerators. They can push a galaxy into a new phase more quickly than it would reach on its own. This is why astronomers pay close attention to galaxies that are in the process of merging. They are natural laboratories for studying how structure, star formation, and black hole growth are linked. In some merging systems, the central regions become incredibly active. Gas funnels inward, feeding the central black hole and triggering a bright, energetic phase known as a quasar or an active galactic nucleus. These objects can be so luminous that they outshine their entire host galaxy. The energy released in this phase can have far-reaching effects. It can heat surrounding gas, drive powerful winds, and even shut down further star formation by removing or dispersing the raw material needed to form new stars. This feedback loop connects the smallest and largest scales within a galaxy. The behaviour of a region no larger than our solar system can influence the fate of a structure that spans tens or hundreds of thousands of light years. Not every merger leads to such extreme activity, but the potential is there, adding another layer of complexity to the story. It is also worth noting that mergers do not always involve similar-sized galaxies. Many interactions are between a large galaxy and a much smaller one. These minor mergers are common and can have cumulative effects. A series of small mergers can gradually build up the mass of a large galaxy, add stars to its halo, and subtly alter its structure. Over time, these small additions can be just as important as the occasional major collision. This gradual growth reinforces the idea that galaxies are not finished objects. They are ongoing projects, shaped by both internal processes and external influences. In the far future, our own galaxy is set to take part in one of these grand events. The Milky Way and the Andromeda Galaxy are moving toward each other at a speed of about 110 kilometers per second. In roughly 4 to 5 billion years, they will begin to interact. The initial pass will likely stretch out long tidal tails and trigger waves of star formation. Over time, the two galaxies will merge into a single, larger system, sometimes called Milkomeda in popular descriptions. From the perspective of any observers who might exist at that time, the night sky would change dramatically. Andromeda would grow larger and brighter in the sky, its structure becoming visible to the naked eye. Eventually, the two star systems would blend, creating a new, reshaped galaxy. This future event connects our local, human-scale experience of the night sky to the vast, ongoing processes that shape the universe. Even though these changes unfold over timescales far longer than any individual life, they are part of the same physical story. The same gravity that keeps your feet on the ground is, on much larger scales, drawing galaxies together. When you think about galaxy collisions and mergers in this way, they start to feel less like rare, catastrophic events and more like a natural part of cosmic life. They are how galaxies grow, change, and sometimes renew themselves. They also remind us that the universe is not static. It is not a finished scene frozen in time. It is a dynamic system, constantly reshaping itself, even if that reshaping is usually too slow for us to notice. It can be enough to hold the image of two galaxies approaching one another in the dark, their shapes slowly stretching and blending, their stars passing by in quiet arcs, their futures becoming intertwined over billions of years. Somewhere within one of those galaxies, on a small planet orbiting an unremarkable star, a listener might be thinking about these distant collisions, while the world around them grows stiller and the night continues its own slow, gentle turn. When you step back from the scale of individual galaxies and let your view widen, something interesting begins to happen. The universe stops looking like a collection of isolated islands and starts to resemble a landscape. Patterns emerge, relationships appear. Galaxies that once felt scattered across the dark begin to reveal that they are, in fact, part of much larger gatherings, linked together by gravity and arranged into structures that stretch across distances almost too large to imagine. This is where the story moves from single galaxies and their local interactions to something far more expansive. This is where clusters, superclusters, and the vast web that connects them come into view. A galaxy cluster is, at its simplest, a family of galaxies bound together by gravity. Instead of orbiting a single central point the way stars orbit the center of a galaxy, the galaxies in a cluster move within a shared gravitational environment. They circle, pass by, and sometimes merge, all while being held together by a mass that is far greater than what we can see with our eyes. Clusters can contain dozens, hundreds, or even thousands of galaxies. Some are relatively small and loose, known as groups, like the one our Milky Way belongs to, often called the local group. Others are massive and dense, with galaxies packed close together and surrounded by vast clouds of hot, thin gas that fills the space between them. If you could drift near a large galaxy cluster, the view would be striking. Instead of a sky dominated by a few thousand visible stars, as it is from Earth, the sky would be filled with galaxies. They would appear as glowing shapes of different sizes and brightnesses scattered across the darkness. Some would be spirals, some smooth and elliptical, some distorted by recent interactions. The background would be rich with light from systems that are themselves composed of billions of stars. At the centre of many large clusters sits a particularly massive elliptical galaxy, often the brightest and largest in the group. These central galaxies can grow to enormous sizes by slowly absorbing smaller galaxies that wander too close. Over time, they become the gravitational anchors of their clusters, surrounded by a swarm of companions. But even this visible population of galaxies is only part of the story. When astronomers measure the motions of galaxies within a cluster, they often find that the galaxies are moving too fast to be held together by the gravity of the visible matter alone. If only the stars and gas we can see were providing the gravitational pull, the cluster should fly apart. The fact that it does not tells us that there is much more mass present than meets the eye. This unseen mass is, once again, dark matter. In fact, clusters of galaxies are some of the best places to study dark matter on large scales. The majority of a cluster's mass is not in its galaxies or in the hot gas between them, but in a vast invisible halo of dark matter that surrounds and permeates the entire system. One of the most striking pieces of evidence for this comes from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, mass warps the fabric of space. Light travelling through this warped space follows curved paths. When a massive object, like a galaxy cluster, lies between us and a more distant galaxy, it can bend and distort the light from that background object. The result can be stretched, magnified, or even duplicated images of distant galaxies appearing as arcs or rings around the cluster. By studying these distortions, astronomers can map out the distribution of mass in the cluster, including the dark matter that cannot be seen directly. These maps often reveal that the dark matter forms a smooth, extended structure that does not always line up perfectly with the visible galaxies. This provides strong evidence that dark matter is a real, separate component of the universe, not just a misinterpretation of how gravity works. Clusters are also filled with another major component that is easy to overlook because it is invisible to the eye. This is the intracluster medium, a vast reservoir of hot gas that permeates the space between galaxies in a cluster. This gas is heated to millions of degrees, causing it to emit X-rays rather than visible light. When astronomers observe clusters in X-rays, they often see a glowing cloud surrounding the galaxies, sometimes containing more mass and gas than in all the stars combined. This gas plays an important role in the life of the cluster. It can strip gas from galaxies that move through it, influencing their ability to form new stars. It can also cool and fall toward the centre, potentially fueling activity in the central galaxy's black hole. The combination of galaxies, dark matter, and hot gas makes a galaxy cluster a complex layered system. It is not just a collection of galaxies, it is an environment with its own internal processes and long-term evolution. Clusters themselves do not exist in isolation. When astronomers map the distribution of clusters across the sky, they find that these massive systems are also arranged in patterns. They tend to be connected by long chains of galaxies, forming larger structures known as superclusters. A supercluster is a group of clusters and galaxy groups linked together over enormous distances, sometimes hundreds of millions of light-years across. These structures are among the largest known in the universe. Our own region of space is part of a supercluster known as Laniakea, a name that means immense heaven. This supercluster includes the Local Group, the Virgo Cluster, and many other groups and clusters of galaxies, all flowing through space in a kind of gravitational current toward a region known as the Great Attractor. The idea of galaxies and clusters flowing may sound strange, but it reflects the fact that, on large scales, the expansion of the universe is not perfectly uniform. Regions with more mass exert a stronger gravitational pull, drawing in surrounding matter. Over time, this creates large-scale patterns of motion and structure. When scientists use computer simulations to model the growth of the universe from its earliest moments, they often start with tiny fluctuations in the density of matter, just slightly more or less dense than average. Under the influence of gravity, these small differences grow. Denser regions pull in more matter, becoming even denser, while less dense regions lose matter and become emptier. Over billions of years, this process leads to the formation of a vast network. Matter gathers into filaments, sheets, and nodes, leaving behind large, empty regions known as voids. Galaxies form and move along these filaments. Clusters form at the intersections, and superclusters emerge as the largest connected regions of this network. This structure is often called the cosmic web. If you could see the universe from far outside, looking at the distribution of galaxies across hundreds of millions of light years, it might look like a three-dimensional spiderweb. Thin threads of galaxies and dark matter would stretch across space, meeting at bright knots where clusters reside. Between them would be wide, dark voids with relatively few galaxies. This web-like pattern is not just a visual metaphor. It reflects the underlying distribution of dark matter, which makes up most of the mass in the universe. Ordinary matter, the stuff that forms stars and galaxies, tends to follow the gravitational scaffolding laid out by dark matter. In this view, galaxies are like beads on invisible strings. They trace out the filaments of dark matter that connect the universe on its largest scales. The cosmic web is not something that can be seen directly with a telescope in the way you might see a single galaxy. It is revealed through large surveys that map the positions of millions of galaxies. By plotting their locations in 3 dimensions, astronomers can reconstruct the large-scale structure of the universe. These maps are some of the most impressive scientific visualizations ever created. They show vast regions of space filled with points of light, arranged into patterns that extend far beyond what any individual observation could reveal. One of the most striking features of these maps is the presence of voids. These are enormous regions of space, sometimes tens or even hundreds of millions of light-years across, that contain very few galaxies. They are not completely empty, but compared to the dense filaments and clusters, they are sparsely populated. Voids are a natural outcome of the way gravity shapes the universe. As matter flows toward denser regions, it leaves behind areas that become progressively emptier. Over time, these voids expand while the filaments and clusters become more pronounced. Galaxies that do form in voids often have different properties from those in dense environments. They may be more isolated, experience fewer interactions, and retain their gas for longer periods. This can lead to differences in star formation rates and overall appearance. This environmental dependence adds another layer to the story of galaxy evolution. A galaxy's fate is influenced not just by its own mass and history, but by where it lives in the cosmic web. Clusters, for example, are often harsh environments for spiral galaxies. The hot gas in the cluster can strip away their own gas. Frequent interactions with other galaxies can disturb their disks. Over time, this can transform spirals into more passive, smooth systems. In contrast, galaxies in the filaments or in more isolated regions may evolve more gently, maintaining their spiral structures and continuing to form stars over longer periods. Superclusters, though, are not permanent bound structures in the same way that clusters are. The expansion of the universe is gradually pulling these enormous systems apart. While clusters remain held together by their own gravity, superclusters are often only loosely connected. Over very long timescales, the expansion of space may overcome the gravitational pull between clusters, causing them to drift apart. This means that the cosmic web itself is a dynamic structure. It grows and changes over time. Filaments can thicken as more matter flows into them. Clusters can merge to form larger clusters. Voids can expand. On the larger scales, however, the pattern remains relatively stable. The overall distribution of filaments and voids changes slowly, shaped by the initial conditions of the universe and the properties of dark matter and dark energy. Dark energy, the mysterious force thought to be driving the accelerated expansion of the universe, adds yet another dimension to this picture. As the expansion speeds up, it becomes harder for gravity to pull distant structures together. This affects how the cosmic web will evolve in the far future. In some models, the universe's expansion will eventually isolate clusters from one another, leaving each cluster as a kind of island universe in an ever-growing sea of empty space. This brings the story full circle in a way. The idea of island universes began as a way to describe individual galaxies. On the larger scales, it may one day apply to entire clusters. There is something quietly poetic about that symmetry, even if it arises from the straightforward application of physical laws. From a more immediate perspective, studying clusters and the cosmic web helps astronomers answer some of the biggest questions in cosmology. How did structure form in the early universe? What is the nature of dark matter? How strong is dark energy? How fast is the universe expanding? By comparing the observed distribution of galaxies and clusters with predictions from theoretical models, scientists can test their understanding of the fundamental components of the cosmos. For example, different types of dark matter would lead to different patterns in the cosmic web. Warm dark matter might smooth out small-scale structures, leading to fewer dwarf galaxies and less fine detail in the filaments. Cold dark matter, which moves more slowly, allows small structures to form more easily, creating a more intricate web. Observations so far tend to favour the cold dark matter model, but the question is not fully settled. New surveys and more precise measurements continue to refine the picture. There is also a human side to this story. The idea that the universe is organised into a vast web of galaxies can change the way we think about our own place in it. We are not just in a galaxy, we are in a group of galaxies, within a cluster, within a supercluster, within a filament of a cosmic web that stretches across the observable universe. Each of these layers adds context, like nested maps showing larger and larger regions. From the perspective of everyday life, this might not seem to matter much. The sky above still looks the same, the stars still form familiar patterns, but in a quieter way, it adds depth to the simple act of looking up. That glowing band of the Milky Way is not just part of a single galaxy, it is part of a group of galaxies, which is part of a supercluster, which is part of a vast network that fills the universe. Somewhere far beyond what you can see with your eyes, there are long chains of galaxies stretching across space, connecting distant clusters in patterns that have been forming for billions of years. If you imagine following one of those filaments, you might picture drifting from one galaxy to another, then to a cluster, then out along another filament, moving through a landscape of light and dark that spans unimaginable distances. The motion along these filaments is slow and steady. Galaxies fall toward clusters. Clusters move relative to one another. The entire web evolves under the combined influence of gravity and cosmic expansion. This slow flow is part of what gives the universe its large-scale character. It is not a random scattering of matter, it is an organised, evolving structure. Not all galaxies move through the universe in the same quiet way. Some of them carry a kind of hidden intensity at their cores, a presence that can shape the light of the entire system and send energy far beyond the boundaries of the stars themselves. These are active galaxies, and at the heart of their activity lies something both simple in concept and profound in effect: a black hole. For a long time, black holes were thought of as rare and exotic objects, the collapsed remains of massive stars that lived and died within galaxies. The idea that something far more massive could sit at the centre of a galaxy, influencing its behaviour on the larger scales, took time to become part of the scientific picture. Today the evidence is strong. Nearly every large galaxy appears to host a supermassive black hole at its core. These black holes are not a few times the mass of the Sun, they are millions or even billions of times more massive. Despite this, they occupy a region of space that is relatively small compared to the size of the galaxy around them. Most of the time, these central black holes are quiet. They sit there, exerting their gravitational influence, while the stars in the galaxy orbit and evolve around them. In these calm phases, the black hole is almost invisible, detectable only through the motions of stars very close to the centre. But sometimes, conditions change. If gas and dust begin to fall toward the black hole, they do not simply drop straight in. Instead, they form a rotating disk of material around it, called an accretion disk. As this material spirals inward, it heats up, releasing enormous amounts of energy. This energy can make the center of the galaxy shine so brightly that it outshines all the stars combined. When this happens, the galaxy becomes active. Active galaxies come in several varieties, but they share this common feature. Their cores are powered by the process of matter falling into a supermassive black hole. The light and energy we see does not come from the black hole itself, which remains dark, but from the hot, glowing material around it. One of the most dramatic examples of this phenomenon is a quasar. Quasars are among the brightest objects in the universe. They can be seen across billions of light years, their light travelling from a time when the universe was much younger. In images, a quasar often looks like a single, bright point of light, similar to a star. But when astronomers study it more closely, they find that this point of light sits at the centre of a distant galaxy. The brightness comes from the active core, not from the galaxy's stars. The energy output of a quasar is staggering. A single quasar can release as much energy as thousands of galaxies like the Milky Way combined. This power comes from the efficiency of the accretion process. As matter falls toward the black hole, a significant fraction of its mass is converted into energy, following the relationship described by Einstein's famous equation, E equals mc squared. This makes black holes some of the most efficient engines in the universe. Active galaxies do not always appear as quasars. In some cases, the active core is less luminous or partially obscured by dust and gas. These galaxies can be classified as Seyfert galaxies, radio galaxies, or other types, depending on their specific properties and how they appear at different wavelengths of light. One of the most fascinating aspects of active galaxies is that their appearance can depend strongly on the angle from which we observe them. Imagine a supermassive black hole at the centre of a galaxy, surrounded by a bright accretion disk and a thick, donut-shaped ring of dust and gas. If we look directly down onto the disk, we might see the full brightness of the active core, and the galaxy could appear as a quasar or a bright Seyfert galaxy. If we look from the side, the dusty ring might block our view of the central region, making the galaxy appear much less active in visible light, even though the same powerful processes are happening inside. This idea, known as the unification model, suggests that many different classes of active galaxies are actually the same kind of object, seen from different perspectives. Another striking feature of many active galaxies is the presence of jets. In some systems, the region around the black hole launches narrow beams of particles and energy that shoot out in opposite directions, perpendicular to the accretion disk. These jets can extend far beyond the galaxy itself, reaching distances of hundreds of thousands or even millions of light years. These jets are most clearly seen in radio galaxies, which emit strong radio waves from the regions where the jets interact with the surrounding intergalactic medium. The exact mechanism that produces these jets is still an area of active research, but it likely involves the intense magnetic fields and rapid rotation near the black hole. When these jets plough into the gas around a galaxy or within a cluster, they can create enormous lobes of radio-emitting material, reshaping the environment on very large scales. This is one of the ways that black holes influence more than just their immediate surroundings. Through jets and radiation, they can affect the distribution and temperature of gas in and around their host galaxies, with consequences for star formation and long-term evolution. The relationship between a galaxy and its central black hole is more than a simple one-way influence. Observations have revealed a strong correlation between the mass of a galaxy's central black hole and the mass of its central bulge of stars. This suggests that the growth of black holes and the growth of galaxies are linked. How this connection works is still being studied, but one idea is that feedback from the active black hole plays a regulating role. When a black hole becomes very active, it can release enough energy to heat or expel gas from the central regions of the galaxy. This reduces the amount of gas available to form new stars, slowing down star formation. Over time, this feedback could help explain why many large galaxies, especially ellipticals, have old stellar populations and little ongoing star formation. The black hole, in this view, acts as a kind of cosmic thermostat, preventing the galaxy from becoming too active for too long. This idea connects the smallest and largest scales in a galaxy in a striking way. The behaviour of matter within a region no larger than our solar system can influence the fate of a system that spans tens of thousands of light years. Not all active galaxies are extreme. Many galaxies go through phases of activity and quiet. A galaxy might be active for a few million or tens of millions of years, then settle back into a quieter state as the supply of gas to the black hole is reduced. These cycles can be triggered by interactions and mergers. When two galaxies pass close to each other or collide, their gravitational forces can drive gas toward their centres. This can feed the central black hole and ignite an active phase. This ties the story of active galaxies back to the broader theme of galaxy interactions and evolution. Mergers do not just reshape the outer structure of galaxies, they can also light up their cores. Looking back in time, astronomers find that active galaxies and quasars were more common in the early universe. This makes sense in the context of galaxy formation. In the early cosmos, galaxies were smaller, more gas-rich, and more likely to interact. There was plenty of material available to feed central black holes. As the universe aged and galaxies used up or lost much of their gas, these active phases became less frequent. Most of the massive black holes we see today are relatively quiet compared to their past selves. In our own galaxy, the central black hole, Sagittarius A, has a mass of about 4 million times that of the Sun. Compared to the black holes in some other galaxies, this is relatively modest. Sagittarius A is currently in a low activity state, emitting only small amounts of radiation. However, evidence suggests that it may have been more active in the past. Observations of large bubble-like structures of high-energy radiation extending above and below the Milky Way's plane indicate that the central black hole may have experienced an active phase millions of years ago, releasing energy that left a lasting imprint on the surrounding gas. This reminds us that even a calm-looking galaxy can carry the marks of a more energetic history. When astronomers study active galaxies across different wavelengths, they uncover a rich and complex picture. In visible light, they might see a bright nucleus and distorted host galaxy. In radio waves, they might trace out long jets and lobes. In X-rays, they can detect hot gas and high-energy regions near the black hole. Each of these views reveals a different aspect of the same underlying process: matter falling into a deep gravitational well and releasing energy as it does so. The study of active galaxies has also played a role in understanding the expansion of the universe. Quasars, because they are so bright, can be seen at great distances. Their light carries information about the conditions of the intergalactic medium along the line of sight, including the distribution of gas and the presence of large-scale structures. By analysing the absorption features in quasar spectra, astronomers can map the cosmic web in a different way, tracing out the filaments of gas that connect galaxies across space. This makes active galaxies not just interesting objects in their own right, but also useful tools for studying the universe on the larger scales. There is also a more conceptual side to this story. Black holes are often portrayed as destructive, as things that swallow and erase. In the context of galaxies, though, they are also creative in a sense. Their energy output can shape the environment, regulate star formation, and influence the long-term structure of their hosts. They are part of a feedback loop that connects gravity, energy, and matter across many orders of magnitude in scale. This does not mean that black holes control everything. Galaxies are complex systems influenced by many factors, including dark matter, gas dynamics, star formation, and interactions with other galaxies. But the presence of a central black hole adds a powerful and often decisive element to that mix. From a human perspective, the idea that something invisible and incredibly dense sits at the heart of a galaxy can feel almost abstract. It is not something you can see directly, at least not in the usual sense, and yet its effects can be traced in the light of stars, in the motion of gas, and in the shape of entire galaxies. If you imagine drifting through a galaxy toward its centre, the view would gradually change. The density of stars would increase. The background glow would become brighter. Near the very core, the environment would be dominated by intense radiation, fast-moving gas, and strong gravitational forces. This region is not a place for stability. It is a place of extremes, and yet, on the scale of the galaxy as a whole, this extreme region is just a small part of a much larger, more balanced system. The vast majority of stars orbit far from the centre, in regions where conditions are far more gentle. This contrast between the calm outskirts and the intense core is part of what gives galaxies their layered character. They are not uniform from centre to edge. Different regions tell different parts of the story. Active galaxies, by highlighting what happens at the centre, draw attention to this inner layer of the galactic structure. They remind us that even in systems that appear quiet and steady from the outside, there can be powerful processes at work beneath the surface. As research continues, astronomers are still refining their understanding of how black holes form and grow in the first place. Did the first black holes form from the collapse of massive early stars, or did they arise from the direct collapse of large clouds of gas? How quickly did they grow? How did they influence the formation of the first galaxies? These questions connect the study of active galaxies to the very beginning of cosmic structure. In the deepest images of the universe, astronomers have found quasars that existed when the universe was less than 1 billion years old. The black holes powering these quasars already had masses of hundreds of millions or even billions of times that of the Sun. This raises an intriguing puzzle. How did such massive black holes form so quickly in the early universe? The answer is not yet fully clear, and it remains an active area of research. This sense of open questions is part of what makes the study of active galaxies feel alive. Even with all the data and models we have, there are still pieces missing from the picture. On a quieter note, it can be interesting to think about how these distant energetic processes relate to the simple act of looking at the night sky. When you see a faint point of light in a telescope image labelled as a quasar, you're seeing the glow of material falling into a black hole billions of years ago in a galaxy so far away that its light has been travelling through space since before the Earth formed. That light has crossed the cosmic web, passed through clusters and filaments, and finally reached your eyes or your screen. In that sense, active galaxies act like beacons, marking out the structure of the universe across time and space. There are times in the life of a galaxy when everything seems to happen at once. After long periods of steady, almost unremarkable star formation, something changes. Gas that has been drifting quietly through the galaxy is suddenly compressed. Clouds collapse more quickly. New stars begin to form at a pace far beyond the usual, lighting up their surroundings and altering the character of the entire system. These are the moments when a galaxy becomes what astronomers call a starburst galaxy, a place of brief but intense brilliance in an otherwise very long and gradual cosmic story. To understand what makes a starburst galaxy special, it helps to think first about how star formation usually works. In most galaxies, stars form in cold, dense clouds of gas, mostly hydrogen, that slowly collapse under their own gravity. This process is steady but not especially fast. A galaxy like the Milky Way forms a few new stars each year, even though it contains hundreds of billions of stars already. From a human perspective, that might sound like a lot, but on galactic timescales, it is a gentle, ongoing process. In a starburst galaxy, that calm pace is replaced by something much more dramatic. These galaxies can form stars tens, hundreds, or even thousands of times faster than a typical spiral galaxy. Instead of a few stars being born each year, entire clusters of massive, bright stars can appear in relatively short periods of time, at least when measured in millions of years rather than billions. This sudden increase in activity does not usually happen without a reason. Starbursts are often triggered by interactions between galaxies. When two galaxies pass close to each other or begin to merge, their gravitational forces can disturb the delicate balance of gas within them. Gas clouds that were once spread out across a disk can be driven inward toward the centre or compressed along spiral arms and tidal features. As these clouds collide and pile up, their density increases. Higher density makes it easier for gravity to take over, and the clouds begin to collapse more quickly, forming new stars at a much faster rate than before. This connection between interaction and starburst activity can be seen in many well-known examples. The antennae galaxies, mentioned earlier as a pair of merging spirals, are also a classic case of a starburst system. The region where the two galaxies overlap is filled with bright young star clusters, glowing in blues and whites that stand out against the darker background of space. Another famous example is the Cigar Galaxy, Messier 82. Its close encounter with its neighbour, Messier 81, has stirred up its gas and triggered an intense wave of star formation in its central region. Images of this galaxy show towering plumes of glowing material being blown out from the core, driven by the combined energy of many massive stars and their eventual supernova explosions. Starbursts can also be triggered by other processes. In some cases, a galaxy might accrete a large amount of gas from its surroundings, such as from the cosmic web or from a smaller companion. This fresh supply of raw material can fuel a new round of star formation. In dense cluster environments, pressure from hot surrounding gas can compress a galaxy's own gas, potentially sparking localized bursts of activity. However they begin, starbursts tend to be relatively short-lived. They burn bright, but they do not last. The reason lies in the nature of the stars they produce. During a starburst, many of the stars that form are massive. These stars shine intensely, producing large amounts of ultraviolet radiation. They also have powerful stellar winds that blow material away from their surfaces. Most importantly, they do not live very long. A massive star may burn through its nuclear fuel in just a few million years, compared to billions of years for a star like the Sun. When these massive stars reach the end of their lives, they explode as supernovae. These explosions release enormous amounts of energy and scatter heavy elements into the surrounding gas. They also heat and disturb that gas, making it harder for it to collapse into new stars. The combined effect of radiation, winds, and supernovae from a large population of massive stars can create a kind of self-regulating mechanism. The very process that drives the starburst can also contribute to bringing it to an end. In some cases, the energy released can push gas out of the galaxy entirely, especially in smaller systems where gravity is not strong enough to hold on to it. These outflows can form large-scale winds, carrying material far into intergalactic space. This means that a starburst galaxy is often a place of both creation and loss. Stars are being born at a rapid pace, but the conditions that allow that birth are being altered, sometimes in ways that make future star formation more difficult. From a visual perspective, starburst galaxies can be striking. They often appear unusually bright for their size. Their light is dominated by young blue stars and glowing clouds of ionized gas. In images, these regions can stand out as vivid patches against the more subdued light of older stars. When observed in infrared light, starburst galaxies can be even more impressive. Much of the energy from young stars is absorbed by surrounding dust and then re-emitted at longer wavelengths. As a result, some starburst galaxies are among the most luminous objects in the universe in the infrared. These systems are sometimes called luminous infrared galaxies, or even ultra-luminous infrared galaxies, depending on how bright they are. Many of them are the products of major galaxy mergers, where the combined gas of two large galaxies has been funneled into a central region, creating an intense dust-enshrouded burst of star formation. Looking at these galaxies in visible light alone can be misleading, because much of the action is hidden behind thick layers of dust. It is only when astronomers use infrared telescopes that the full scale of the starburst becomes apparent. In the early universe, starburst activity appears to have been more common. young galaxies were smaller, richer in gas, and more likely to interact with one another. As a result, bursts of rapid star formation were a regular part of galaxy growth. Some of the most distant galaxies observed today, seen as they were billions of years ago, show signs of intense star formation. They appear as compact, bright objects, often with irregular shapes and clumpy structures. These early starbursts likely played a major role in building up the stellar mass of the first large galaxies. By studying these distant systems, astronomers can piece together how galaxies assembled their stars over cosmic time. They can see when most of the star formation occurred and how it varied with environment and galaxy type. In more recent times, starburst galaxies are less common, but they still occur, often in specific situations. Major mergers between large gas-rich galaxies are one of the most reliable ways to trigger a powerful starburst in the present-day universe. These events are relatively rare, but when they happen, they can transform both galaxies involved. The starburst can consume a significant fraction of the available gas, leaving behind a system that is more massive, more evolved, and often less capable of forming new stars in the future. This connects starbursts to the broader story of galaxy evolution. They are not just isolated episodes. They are part of the way galaxies grow and change. A galaxy might begin its life as a small gas-rich system, forming stars steadily. Over time, it might experience one or more interactions that trigger bursts of activity. These bursts can rapidly build up its population of stars and alter its structure. Eventually, the galaxy may run low on gas and settle into a quieter, more passive phase. In this sense, starbursts can be seen as milestones in a galaxy's life, moments when a lot of change happens in a relatively short time. There is also a close relationship between starbursts and active galactic nuclei. In some galaxies, the same inflow of gas that fuels a burst of star formation can also feed the central black hole. This can lead to a phase where the galaxy is both a starburst and an active galaxy at the same time. In these systems, energy is being released both by massive young stars and by the accretion process around the black hole. The combined effects can be dramatic, driving powerful winds and shaping the galaxy's future. Disentangling the contributions of star formation and black hole activity is one of the challenges in studying these galaxies, especially when much of the action is hidden behind dust. Starburst galaxies also play an important role in enriching the universe with heavy elements. The massive stars formed during a burst live fast and die young, exploding as supernovae that create and disperse elements like oxygen, carbon, and iron. These elements become part of the surrounding gas, eventually incorporated into new generations of stars and in some cases planets. Over time, starbursts can significantly raise the metal content of a galaxy and its surroundings. The outflows driven by starbursts can carry these elements far beyond the galaxy itself, contributing to the chemical enrichment of the intergalactic medium. This means that starburst galaxies can influence not just their own evolution, but also the broader environment around them. In a way, they act as engines of change, spreading the products of stellar evolution across large regions of space. When astronomers observe starburst galaxies across different wavelengths, they see a layered picture. In ultraviolet and visible light, young stars and glowing gas dominate. In infrared, warm dust reveals where star formation is hidden from view. In radio waves, astronomers can trace cold gas, the raw material for future stars. In X-rays, they can detect the hot gas heated by supernova explosions and stellar winds. Each of these views adds another piece to the story of what is happening inside these active systems. From a theoretical perspective, starbursts provide important tests for models of star formation and feedback. The extreme conditions in these galaxies push physical processes to their limits. Gas densities are high, radiation fields are intense, supernova rates are elevated. By comparing observations with simulations, scientists can learn how well their understanding of these processes holds up under such conditions. One of the questions that arises in this context is how efficient star formation can become. In a typical galaxy, only a small fraction of the available gas is turned into stars over a given period. In a starburst, that fraction can be much higher. Understanding what sets this efficiency and what ultimately limits it is part of the broader effort to understand how galaxies convert gas into stars across the universe. There is also a more subtle, almost philosophical aspect to starburst galaxies. They highlight the idea that not all change in the universe is slow and gradual. Even on cosmic timescales, there are moments of intensity, periods when things happen more quickly, when structures are built and transformed at an accelerated pace. These moments are still long compared to a human lifetime, but in the context of billions of years, they stand out as relatively brief flashes of activity. If you imagine watching a galaxy over the entire span of its existence, a starburst might appear as a bright flare in its light curve, a spike in its history, followed by a return to a more subdued glow. This perspective can make starbursts feel like punctuation marks in the long sentence of cosmic evolution. On a quieter level, it can be interesting to think about what a night sky inside a starburst galaxy might look like. The density of young, bright stars would be higher. The light from glowing gas clouds would be more prominent. The background might feel more crowded, more luminous. At the same time, dust and gas might obscure large regions, creating dark patches and glowing edges where light breaks through. The sky could be a mix of brilliance and shadow, shaped by the same processes that are building the galaxy's future. These internal views are, of course, imagined, but they remind us that each galaxy, each phase of its life, carries its own local environment, its own version of a sky. Starburst galaxies, with their brief moments of brilliance, connect the small-scale physics of star formation to the large-scale story of galaxy growth. They show how interactions, gas dynamics, and feedback can come together to create episodes of rapid change. They also reinforce the idea that galaxies are not static objects. They are dynamic systems, capable of shifting between different modes of behavior over time. For now, though, it can be enough to hold the image of a galaxy in the midst of a bright, energetic phase, its stars being born in great clusters, its gas clouds glowing and shifting, its light briefly intensified before the long, quieter chapters of its life resume. Somewhere far away, such a galaxy is shining more brightly than it will for most of its existence, its moment of brilliance travelling through space, crossing billions of light years, eventually becoming a faint, gentle glow in a telescope image, and perhaps a quiet thought in the mind of someone listening under a dark, peaceful sky. Long before any telescope was pointed at the sky, the idea of distance was already woven into the way people thought about the stars. Some lights felt close, others felt far, and beyond them all was a kind of imagined boundary, a place where sight and knowledge simply ran out. For most of human history, that boundary felt fixed. The night sky was deep, but not endlessly deep. There were only so many stars you could see, only so many points of light to wonder about. As telescopes grew more powerful, that sense of a boundary began to soften. Each new instrument pushed the edge a little farther back. Faint stars appeared where there had been darkness. Smudges of light resolved into galaxies. Galaxies turned out to be just one layer in a much larger structure. The universe kept opening up, not in a sudden reveal, but in a series of quiet, patient steps. The deepest surveys of the sky represent the latest of those steps. They are the result of astronomers deciding very deliberately to stare at a single small patch of sky for a very long time, collecting as much light as possible from whatever happens to be there. The idea is simple. If you look long enough, faint things become visible. One of the most famous examples of this approach is an image known as the Hubble Deep Field. In the mid-1990s, astronomers pointed the Hubble Space Telescope at a region of sky that appeared, at first glance, almost empty. It was a tiny area, about the size of a grain of sand held at arm's length. For days, Hubble gathered light from that spot. When the data were combined into a single image, the result was surprising and for many people quietly astonishing. Instead of emptiness, the image was filled with galaxies, hundreds of them, each one a collection of billions of stars, each one at a different distance, and therefore at a different moment in cosmic history. That small patch of sky turned out to be a window into the deep past. What made this especially striking was not just the number of galaxies, but their variety. Some looked like familiar spirals, some were smooth and elliptical, others were small, clumpy and irregular, shapes that did not fit neatly into any category. This mix reflected the fact that when you look far away, you're also looking back in time. Light takes time to travel. The farther an object is, the longer its light has been on its way to you. In the case of the most distant galaxies in the Hubble Deep Field, that light began its journey when the universe was only a small fraction of its current age. In those early times, galaxies were still forming. They had not yet settled into the well-organised shapes that are more common nearby. The deep field images offered a kind of visual timeline, showing galaxies at many different stages of development all in the same frame. This idea that a single image can contain multiple eras of cosmic history is one of the most quietly powerful aspects of deep surveys. You're not just looking at a collection of distant objects, you're looking at a cross-section of time. After the success of the original Hubble Deep Field, astronomers created even deeper and more detailed images. The Hubble Ultra Deep Field, for example, was the result of hundreds of hours of observation, focused on an even smaller area of sky. The final image revealed thousands of galaxies, some so faint and distant that they pushed the limits of what the telescope could detect. In that image, the sky seems almost crowded. Every dark patch, every empty-looking space on closer inspection contains a faint smudge of light that turns out to be another galaxy. This can change the way you think about the night sky. The stars you see with your eyes are just the nearest layer. Behind them, in every direction, there are galaxies stacked across billions of light years, most of them far too faint to see without powerful instruments and long exposures. The idea of an edge of sight, then, is not a hard boundary. It is more like a fading. As you go farther out, objects become dimmer and harder to detect. The universe does not suddenly stop. It just becomes more difficult to observe. The faintest galaxies in these deep surveys are often very small and very distant. Some appear as tiny red dots, their light stretched to longer, redder wavelengths by the expansion of the universe. This stretching, known as redshift, is one of the key tools astronomers use to measure how far away a galaxy is and how long its light has been travelling. The higher the redshift, the farther back in time you're looking. By analysing the colours and spectra of these distant galaxies, astronomers can estimate their ages, their rates of star formation, and their chemical compositions. This allows them to build a picture of how galaxies have changed over the history of the universe. One of the things that emerges from this work is that the early universe was a much more active place in terms of galaxy growth. Star formation rates were higher, interactions and mergers were more common. Galaxies were, on average, smaller and more irregular. The deep surveys show many galaxies that look like collections of bright clumps rather than smooth, coherent structures. These clumps are often regions of intense star formation, suggesting that early galaxies grew by forming stars in localized bursts that gradually built up a larger system. Over time, as galaxies merged and accumulated more mass, their structures became more stable. Disks formed. Bulges grew. The familiar shapes of spirals and ellipticals became more common. This transition is not something you can see in a single image, but by comparing deep surveys at different depths and in different parts of the sky, astronomers can trace how the population of galaxies changes with distance and time. Another important development in deep surveys has been the use of telescopes that observe in wavelengths beyond visible light. The Hubble Space Telescope, for example, can see into the near-infrared, which is especially useful for studying very distant galaxies whose light has been redshifted out of the visible range. More recently, the James Webb Space Telescope has taken this approach even further. With its larger mirror and sensitivity to longer wavelengths, it can detect galaxies that formed even earlier in the universe's history, potentially within the first few 100 million years after the Big Bang. Early images from this telescope have revealed galaxies that appear surprisingly bright and well formed for their age. This has sparked new discussions about how quickly galaxies can grow and how early massive systems can form. These observations are a reminder that the edge of sight is not just a technical limit, it is also a conceptual frontier. Each time we push it back, we find something that challenges or refines our understanding of how the universe works. The deepest surveys also help address a simple but profound question: how many galaxies are there? At first, the answer seems straightforward. Count the galaxies in a deep field, estimate how representative that patch of sky is, and scale up to the whole sky. Early estimates based on Hubble data suggested that there are on the order of hundreds of billions of galaxies in the observable universe. Later studies, taking into account the faintest and smallest galaxies that are hardest to detect, have suggested that the number could be closer to a couple of trillion. This is not a number that can be pinned down easily. It depends on how you define a galaxy, how faint an object you include, and how you account for galaxies that are beyond current detection limits. Deep surveys play a crucial role in this process. They reveal the population of faint galaxies that dominate the total count, even though each one contributes very little light. In a way, most of the galaxies in the universe are small, faint, and unremarkable on their own. It is only when you consider them together that their sheer number becomes impressive. There is also a kind of humility in that realization. The grand, bright galaxies that dominate popular images are, in terms of numbers, a minority. The universe is mostly made up of quiet, modest systems that drift through space without drawing much attention. Another aspect of deep surveys is their role in mapping the large-scale structure of the universe. By measuring the distances to thousands or millions of galaxies, astronomers can build three-dimensional maps that show how galaxies are arranged across vast regions of space. These maps reveal the same cosmic web pattern seen in simulations and smaller-scale studies. Filaments of galaxies stretch across space, clusters sit at the intersections, voids open up in between. At great distances, these structures appear smaller and less developed, reflecting the fact that the universe was younger and less evolved at those times. By comparing the structure at different distances, astronomers can study how the cosmic web itself has grown over time. This connects the deepest surveys to some of the most fundamental questions in cosmology. How did the initial fluctuations in the early universe grow into the large-scale structure we see today? What role did dark matter play in shaping that structure? How is the expansion of the universe affecting the growth of clusters and filaments? The galaxies at the edge of sight are not just distant objects. They are data points in a much larger effort to understand the history and composition of the cosmos. There is also a more subtle, almost personal side to these images. When you look at a deep field image, you are seeing light that has been travelling for billions of years. Some of it left its source before the Earth existed. Some of it left before the sun formed. That light has crossed expanding space, passed by countless galaxies, moved through regions of gas and dust, and finally reached a telescope, where it was captured and turned into a picture. The image itself is a kind of time capsule. It contains information from many different eras, all compressed into a single frame. This can make the idea of the present moment feel a little different. The light reaching you now is always a mix of pasts. The farther you look, the deeper into that mix you go. Deep surveys also highlight the limits of our instruments and our methods. Even the most powerful telescopes cannot see everything. There will always be galaxies that are too faint, too small, or too distant to detect. Some of these galaxies may exist beyond the observable universe, in regions of space from which light has not had time to reach us since the Big Bang. Others may simply be below the sensitivity of current technology. This means that our picture of the universe, no matter how detailed it becomes, is always incomplete in some way. We see a portion of what exists, shaped by the speed of light, the age of the universe, and the capabilities of our tools. In this context, the phrase edge of sight takes on a layered meaning. It refers not just to a physical distance, but to the boundary of what we can know through observation. As technology advances, that boundary moves. New telescopes, new detectors, and new analysis techniques push it outward, revealing objects and structures that were previously hidden. This process is ongoing. Planned and proposed observatories aim to survey the sky in new ways, at different wavelengths and with greater sensitivity. Each one will add another layer to the picture. At the same time, deep surveys are not just about looking farther, they are also about looking more carefully. By studying the same regions of the sky over long periods, astronomers can detect subtle changes, such as the movement of nearby objects, the flickering of distant active galaxies, or the appearance of supernovae in faraway systems. These time-based studies add another dimension to the static images, turning deep fields into dynamic records of change as well as distance. The galaxies at the edge of sight often look very different from those nearby. They are smaller, less structured, and more compact. This reflects the fact that they have had less time to grow and evolve. But even among these early systems, there is diversity. Some appear to be rapidly forming stars. Others look more settled. Some are isolated. Others are part of small groups. This variety suggests that even in the early universe, galaxy formation was not a single, uniform process. Different regions and different conditions led to different outcomes. Understanding this diversity is part of the challenge of modern astronomy. It requires combining observations, simulations, and theory to build a coherent picture of how galaxies form and change across cosmic time. The deepest surveys also help refine measurements of the universe's expansion. By studying distant galaxies and supernovae, astronomers can trace how the expansion rate has changed over time, providing clues about the nature of dark energy. In this way, the faintest, most distant galaxies contribute to answering some of the biggest questions about the fate of the universe. All of this scientific detail sits alongside a simpler, quieter impression. A deep field image is, at its core, a picture of a very small piece of the sky, a piece that, if you looked at it with your eyes alone, would seem empty. That contrast between what we see unaided and what is revealed with long, careful observation is part of what gives these images their quiet impact. It suggests that the universe is fuller, richer, and more layered than it appears at first glance. That behind every patch of darkness, there is more light, more structure, more history. This idea can extend beyond astronomy. It can serve as a gentle reminder that there is often more present than what is immediately visible in many different contexts. Returning to the cosmic scale, the galaxies at the edge of sight represent the earliest chapters of the story being told throughout this journey. They are the ancestors of the spirals, ellipticals, irregulars, dwarfs, starbursts, and active galaxies seen closer to home. By studying them, astronomers are, in a sense, reading the opening lines of the universe's long narrative. Those opening lines are not simple. They are filled with rapid change, intense activity, and the first steps toward the complex structures that would come later. For now, it can be enough to rest with the idea of a telescope quietly gathering light from a tiny patch of sky, hour after hour, night after night, drawing in photons that have been travelling across space for billions of years. Those photons come together to form an image that is, in its own quiet way, a map of time, showing where galaxies were long before there were eyes to see them. Somewhere, in that dense field of distant light, are the faint beginnings of systems that would eventually grow into the kinds of galaxies that fill the nearby universe. After looking at enough images of distant galaxies and reading enough numbers that stretch into the billions and trillions, a natural question begins to take shape. How many of these systems are actually out there? Not just the ones we can see in a telescope image, or the ones catalogued in a database, but all of them, across the entire observable universe. How many separate collections of stars, gas, and dark matter exist, drifting through space, each with its own history, structure, and future. It sounds like the kind of question that should have a clean, simple answer, a number you can write down, underline, and move on from. In practice, it turns out to be one of the most fluid and quietly complicated questions in modern astronomy. One of the reasons it is so challenging is that the universe does not present itself to us all at once. We do not have a map that shows every galaxy from one edge of the observable cosmos to the other. What we have instead are samples, deep surveys that look at small patches of sky, wide surveys that cover larger areas but to shallower depths, different instruments that see different wavelengths of light and reveal different kinds of objects. Each of these views gives a partial picture, and each one has to be carefully interpreted and combined with the others to build up a broader understanding. The basic method for estimating the number of galaxies is in principle straightforward. You count how many galaxies you see in a small representative area of the sky. You figure out how deep that survey goes, meaning how faint and how distant the galaxies are that it can detect. Then you use that information to estimate how many galaxies there would be across the entire sky and out to the same distance. This is essentially a cosmic version of taking a small sample and scaling it up. But every step of that process involves assumptions and uncertainties. The first challenge is deciding what counts as a galaxy in the first place. This might seem obvious at first. A galaxy is a collection of stars bound together by gravity. But when you start dealing with very small, faint and distant objects, the line between a galaxy and something else can become blurred. Some of the faintest objects detected in deep surveys are only a few hundred light-years across and contain relatively few stars. Are these truly separate galaxies, or are they star clusters or fragments of larger systems? Different definitions can lead to different counts. There are also objects that are in the process of becoming galaxies or in the process of being torn apart. Do you count them as galaxies? The answer depends on the criteria you choose. Then there is the issue of brightness. Most of the galaxies in the universe are not bright, large spirals or ellipticals like the ones that tend to appear in popular images. They are small and faint, often dwarfs that emit very little light. Even in the deeper surveys, there will be galaxies that are too faint to detect. Their stars may be few, their light spread out over a large area, making them blend into the background. This means that any count based on observations has to account for the galaxies that are likely missing from the data. Astronomers use models and statistical techniques to estimate how many faint galaxies there should be based on the ones they can see, but this introduces another layer of uncertainty. Despite these challenges, scientists have made progress over the years. Early estimates based on surveys from telescopes like Hubble suggested that there are on the order of a few 100 billion galaxies in the observable universe. As deeper and more sensitive surveys became available, that number increased. Studies that took into account the likely population of faint dwarf galaxies suggested that the total could be closer to 2 trillion. This was a striking result. It implied that most galaxies in the universe are small and faint, and that the large bright ones we are most familiar with are just the tip of the iceberg. But even that number is not fixed. One reason the number keeps changing is that our ability to detect galaxies keeps improving. Each new generation of telescopes can see fainter and more distant objects. The James Webb Space Telescope, for example, has already revealed galaxies that formed very early in the universe's history and that were beyond the reach of previous instruments. As these new observations come in, they can add to the known population, especially at the faint and distant end. Another reason is that the universe itself is changing. Galaxies do not simply exist in a steady state. They form, they grow, they merge, and sometimes they are destroyed or absorbed into larger systems. Over cosmic time, the number of separate galaxies can go up or down depending on which processes dominate. In the early universe, there were likely many more small separate systems. As time went on, gravity pulled these systems together, mergers became common, small galaxies combined to form larger ones. This means that, in a sense, the total number of galaxies has probably decreased over time, even as the average size and mass of galaxies has increased. So when you ask how many galaxies exist, you also have to ask when. The answer for the universe as it is now will be different from the answer for the universe as it was 10 billion years ago. This time dependence adds another layer of complexity. The deep surveys that look far away are showing you the universe at earlier stages. The galaxies in those images are not just distant, they are younger. Some of the small, faint objects seen in deep fields may not survive as separate galaxies to the present day. They may merge with others, becoming part of larger systems. In that sense, a deep field image can contain a larger number of galaxies than a comparable volume of space in the nearby universe, simply because more of them have not yet merged. This highlights an important idea. The number of galaxies is not a static property of the universe. It is a dynamic quantity, shaped by the ongoing process of structure formation. There is also the issue of the observable universe itself. The universe is about 13.8 billion years old. Light travels at a finite speed. This means that there is a limit to how far we can see, known as the observable horizon. Beyond that horizon, there may be more galaxies, but their light has not had time to reach us yet. When astronomers estimate the total number of galaxies, they usually mean the number within the observable universe. This is not necessarily the same as the total number of galaxies in the entire universe, if the universe extends beyond what we can observe. Some cosmological models suggest that the universe could be much larger than the observable region, possibly even infinite. If that is the case, then the total number of galaxies could also be far larger, perhaps infinite as well. This moves the question into a more philosophical territory. There may be a practical limit to what can be counted or even meaningfully defined. Within the observable universe, though, the question remains grounded in data and models. Another factor that affects galaxy counts is how surveys are conducted. Some surveys focus on specific wavelengths of light. Others cover specific areas of the sky. Each choice influences which galaxies are most easily detected. For example, a survey in visible light may miss galaxies that are heavily obscured by dust, or that are very distant and whose light has been shifted into the infrared. An infrared survey may reveal those objects, but might be less sensitive to others. Radio surveys can detect galaxies that are rich in cold gas, even if they are faint in visible light. By combining data from different types of surveys, astronomers can build a more complete picture of the galaxy population. But this process is complex and ongoing. There is also the challenge of distinguishing galaxies from other sources of light. In deep images, faint stars in our own galaxy can sometimes appear similar to distant galaxies. Sophisticated analysis is needed to separate these populations. Even with all these tools, there is always a margin of uncertainty. The changing number of galaxies also reflects changes in how astronomers define and classify them. As new types of objects are discovered, the boundaries of what is considered a galaxy can shift. For example, the discovery of ultra-diffuse galaxies, which are large in size but very faint, has added a new category to the mix. These systems can be as wide as the Milky Way, but contain far fewer stars, making them difficult to detect. There are also compact, dense systems that blur the line between star clusters and small galaxies. Each of these discoveries forces a re-examination of definitions and counts. Another reason the number keeps changing is that theoretical models are continually being refined. Simulations of galaxy formation based on different assumptions about dark matter, dark energy, and the physics of gas and star formation can predict different numbers of galaxies, especially at the small, faint end. By comparing these predictions with observations, astronomers can test and improve their models. If a model predicts many more small galaxies than are observed, that might indicate that some process, such as feedback from star formation or black holes, is suppressing the formation of stars in those systems. This back and forth between theory and observation is part of what drives progress in the field. The number of galaxies is not just a statistic, It is a constraint on our understanding of how the universe works. There is also a connection between galaxy counts and the distribution of dark matter. In many models, each galaxy forms within a halo of dark matter. The number of dark matter halos of different sizes predicted by simulations can be compared with the number of galaxies observed. Discrepancies between these numbers can point to gaps in our understanding, either in the nature of dark matter or in the processes that turn dark matter halos into visible galaxies. This ties the simple-sounding question of how many galaxies there are to some of the deepest questions in physics. On a more practical level, the way astronomers present these numbers can influence how they are perceived. Saying there are hundreds of billions of galaxies is already hard to grasp. Saying there are 2 trillion makes the scale feel even more overwhelming. But both numbers are, in a sense, approximations. They are not precise counts. They are best estimates, based on the data and models available at the time. As those data and models change, so does the estimate. This can give the impression that scientists are unsure or that the numbers are unstable. In reality, it reflects the fact that the frontier of observation is still moving. Each new telescope, each new survey, extends our reach and refines our understanding. It is also worth remembering that even if we had a perfectly accurate count of galaxies in the observable universe, that number would still be a snapshot. It would represent the universe at a particular stage in its evolution. Billions of years ago, the number would have been different. Billions of years in the future, it will be different again. This temporal aspect adds a kind of depth to the question. You're not just asking how many galaxies there are. You're asking how the universe's population of galaxies has changed and will continue to change over time. There is a quiet parallel here with other kinds of counts, counting stars in a galaxy, counting trees in a forest, counting people in a city. In all these cases, the number is not fixed. It changes as things grow, combine, and disappear. The difference, of course, is scale. On the scale of the universe, the processes that change the count operate over billions of years and across distances that stretch the imagination. Another interesting aspect of galaxy counts is how they relate to the idea of typicality. If most galaxies are small and faint, then a large, bright spiral like the Milky Way may be less typical than we often assume. This can influence how astronomers think about the conditions needed for things like star formation, planet formation, and by extension, the potential for life. If the majority of galaxies are dwarfs with low metal content and different environments, then the conditions we experience in the Milky Way may not be the most common ones in the universe. This does not necessarily mean that life is rare or common. It simply adds another layer to the context in which those questions are asked. The sheer number of galaxies also has a psychological effect. It can make the universe feel vast and impersonal. At the same time, it can make any individual galaxy, including our own, feel like a small part of a much larger whole. Yet, from within a galaxy, that galaxy is the entire universe. All the stars you can see with your eyes belong to it. All the history of life on Earth has unfolded within it. This contrast between the local and the global is part of what gives the study of galaxies its particular flavour. You move back and forth between the familiar and the almost inconceivably large. Returning to the technical side, there are ongoing efforts to improve galaxy counts by combining data from multiple surveys and using sophisticated statistical methods. These efforts aim to account for selection effects, detection limits, and cosmic variance, which is the idea that different regions of the universe may not be perfectly representative of the whole. By observing many different patches of the sky, astronomers can average out these regional differences and get a more reliable estimate. Even so, there will always be a degree of uncertainty. Some galaxies will remain beyond detection, some definitions will remain fuzzy, some theoretical questions will remain open. In that sense, the number of galaxies is not just a number. It is a reflection of the current state of our knowledge. As that knowledge grows, the number will continue to be revised. There is also something quietly satisfying about the fact that this question, does not have a final, closed answer. It mirrors the nature of the universe itself, which is not a finished object, but an ongoing process. Galaxies are still forming, they are still merging. New light is still being emitted, travelling across space toward future observers. The deep surveys of today will become the baseline for the discoveries of tomorrow. The galaxies that are now at the edge of sight may become familiar objects as technology advances, and beyond them there will likely be more, waiting in the faint, distant background, just out of reach for now. On a quieter note, it can be interesting to imagine what it would mean, on a personal level, to truly grasp the scale implied by these numbers. Hundreds of billions, trillions. Each of those galaxies contains billions of stars. Around some of those stars there are likely planets. On some of those planets, there may be environments as complex and varied as the one on Earth. This line of thought can quickly spiral into speculation, but it also grounds the abstract numbers in something more tangible. The question of how many galaxies exist becomes, indirectly, a question about how much potential there is in the universe for different kinds of worlds and stories. But even if you set those speculations aside, the simple fact of the number remains striking. The night sky, which to the naked eye contains only a few thousand stars, is in reality a window into a universe filled with more galaxies than there are grains of sand on many beaches. Most of those galaxies will never be seen directly by human eyes. They will remain as faint points in images, or as entries in catalogues, or as statistical contributions to a total count. And yet, they are there, each one a system with its own internal motions, its own cycles of star birth and death, its own place in the cosmic web. At some point, after moving through spirals and ellipticals, through clusters and deep fields, through numbers that climb into the trillions and distances that stretch across billions of light years, it becomes natural to pause and turn the view back inward. Not back to the centre of a galaxy or the heart of a cluster, but back to a much smaller place. Back to where you are right now, listening, breathing, resting under a sky that feels quiet and familiar, even though it is part of something unimaginably vast. All of these galaxies, all of this structure and motion and history raises a gentle question. What does any of it mean for us here and now? From a strictly physical point of view, the connection is simple. The same laws that govern the motion of galaxies govern the fall of an apple, the flow of air into your lungs, the rhythm of your heartbeat. Gravity, electromagnetism, the behaviour of atoms and energy, all of it follows the same basic rules, whether it's happening in a distant quasar or in the room where you're sitting. The elements that make up your body were formed in stars. Hydrogen and helium came from the earliest moments of the universe. Heavier elements like carbon, oxygen and iron were forged in the cores of stars and scattered into space by supernova explosions. Over time, those elements became part of clouds of gas that formed new stars and planets, including the one you are on now. In that sense, the story of galaxies is not separate from the story of life on Earth. It is the long prelude. But beyond that physical connection, there is a quieter, more reflective layer. Knowing that the universe contains not just one galaxy, but hundreds of billions or trillions of them, can change the way you think about scale and place. The Milky Way, which once seemed like the entire universe, becomes one among many. The Sun, which once seemed like a central defining feature, becomes one star among hundreds of billions in a single galaxy, which itself is one among countless others. This shift in perspective can feel humbling. It can make human concerns seem very small against such a vast backdrop. A single day, a single life, even a single civilization, occupies only a tiny moment in cosmic time and a tiny point in cosmic space. But that is not the only way to see it. Another way to look at it is to notice that despite this vastness, you are here, able to think about it. Out of all this matter and energy, arranged across immense distances and times, there has emerged a place where the universe can, in a sense, become aware of itself. When you look at an image of a distant galaxy, the light in that image began its journey billions of years ago. It crossed expanding space, passed through the cosmic web, and eventually reached a telescope on or near Earth. From there, it was turned into a signal, a picture, and finally something you can see and think about. That chain of events links a distant corner of the universe to a moment in your own experience. This does not give that moment any special cosmic importance in a physical sense. The universe does not seem to revolve around observers, but it does give the act of observing a certain quiet significance. The universe is vast and complex, and within it, there are small pockets where that complexity can be noticed, studied, and reflected upon. Galaxies, in this context, become more than just objects of study. They become part of a larger story about curiosity, knowledge, and the desire to understand where we are and how we fit into what surrounds us. There is also a practical side to this connection. The study of galaxies has driven the development of technologies that have found their way into everyday life. Advances in imaging, data processing, and materials science, developed in part to build better telescopes and detectors, have influenced fields ranging from medicine to communications. The effort to understand the universe has, in many ways, helped shape the tools we use to navigate our own world. On a cultural level, galaxies have become part of how we imagine the universe. They appear in art, in literature, in music, in stories about exploration and possibility. The idea of countless star systems spread across a vast cosmic web feeds the human tendency to wonder about what might exist beyond our own experience. This does not require any specific belief about life elsewhere. It simply reflects the fact that when you learn that the universe is large and diverse, it naturally invites you to imagine variety and potential on many levels. At the same time, the immensity of the cosmos can highlight the fragility of our own environment. Earth is a small, thin layer of life on the surface of a rocky planet, orbiting an ordinary star in the outskirts of a galaxy that is itself one among many. From a cosmic perspective, there is nothing especially protected or guaranteed about this arrangement. The conditions that allow life to exist here are the result of a long chain of events, from the formation of elements in ancient stars to the assembly of a stable planetary system. This awareness can bring a different kind of appreciation for the world close at hand. The sky above, the ground beneath, the air you breathe, all of it exists within a much larger context that makes it, in a way, both ordinary and rare at the same time. Galaxies also remind us of time on a scale that is very different from the one we usually live with. The processes that shape galaxies unfold over millions and billions of years. Star formation, mergers, the growth of black holes, the expansion of clusters, all of these happen so slowly that, from a human perspective, they might as well be frozen. And yet, they are not frozen. They are ongoing. When you look at a galaxy, you're seeing it as it was in the past. The light has taken time to reach you. Even the light from the nearest stars takes years to arrive. The light from distant galaxies takes millions or billions of years. This means that the sky is, in a very literal sense, a record of history. Every point of light is a message from another time. This can change the way you think about the present. The moment you're in now is always layered on top of countless pasts, just as the light reaching you is layered from different eras. In everyday life, time often feels like something that moves too quickly. Days pass, weeks pass, years pass. Against the backdrop of galactic timescales, those spans are incredibly brief. But that does not make them meaningless. It simply places them in a different frame. The universe is old. It has been around for billions of years. It will likely continue for billions more. Within that long story, each small moment still has its own weight, its own experience. There is also something quietly grounding about the idea that, no matter how complex or distant the universe becomes in our understanding, it is still governed by a relatively small set of underlying principles. The same physics that describes the behavior of a distant galaxy describes the behavior of the matter in your own body. The same gravity that draws galaxies together is the gravity that keeps you connected to the Earth. This continuity can make the vastness feel a little less alien. The universe is large, but it is not arbitrary. It follows patterns and rules that can be learned, tested, and understood, at least in part. The study of galaxies is one expression of that larger human project, the attempt to make sense of the world and the cosmos beyond it. On a quieter, more personal level, thinking about galaxies can offer a kind of mental space. When you imagine the scale of the universe, the long arcs of time, the slow movements of matter across enormous distances, everyday concerns can sometimes feel a little lighter. This does not solve problems or remove difficulties, but it can provide a different perspective. It can remind you that the world is larger than any single moment, any single worry, any single story. That perspective can be calming in its own way. At the same time, it can also sharpen the sense of what is close and immediate. The vastness of the universe does not diminish the value of the people and places near you. If anything, it can make those connections feel more distinct, more specific, more worth noticing. Out of all the possible places in all the possible galaxies, this is where you are. There is also a kind of continuity in the way galaxies and human cultures both build on the past. Galaxies grow by merging smaller systems, by incorporating material that has already been shaped by earlier processes. Human knowledge grows in a similar way, building on observations, ideas, and discoveries made by those who came before. The deep field images, the surveys, the models, all of them are the result of many generations of people asking questions, building instruments, and sharing what they learned. When you hear about a distant galaxy or a new discovery, you are connected indirectly to that long chain of curiosity and effort. This can give the study of the universe a kind of human dimension that sits alongside the scientific one. There is also an interesting contrast between the stability and the change you see when you look at galaxies. On one hand, galaxies persist for billions of years. They are long-lived structures. On the other hand, they are constantly changing, even if that change is slow. Stars are being born and dying. Gas is moving. Galaxies are merging. Clusters are forming. The cosmic web is evolving. This mix of continuity and transformation can feel familiar on a smaller scale. Many things in life have a similar pattern. There are structures and routines that persist, and within them there is constant subtle change. Seeing that pattern reflected on a cosmic scale can make it feel like part of a larger, more universal process. The question of what all these galaxies mean does not have a single, definitive answer. It depends on what you are looking for in the question. If you're looking for a scientific answer, they mean data, structure, and a way to test theories about how the universe works. If you are looking for a philosophical answer, they mean scale, context, and a reminder of how small and how connected we are at the same time. If you're looking for a more personal answer, they might mean a sense of wonder or calm or curiosity, or simply a way to step outside of the usual flow of thoughts for a moment and think about something larger. All of these layers can exist at once. It is also worth noticing that our understanding of galaxies is still incomplete. Even after centuries of observation and decades of modern astrophysics, there are many open questions. We still do not fully understand what dark matter is, even though it plays a major role in shaping galaxies and clusters. We are still learning how the first galaxies formed, how quickly black holes grew, and how the balance between star formation and feedback evolves over time. This means that the story of galaxies is not finished. It is still being written, not in the sense that the universe is waiting for us to observe it, but in the sense that our understanding of it is still growing. Future telescopes will see farther. New instruments will measure things in more detail. New models will be developed to explain what is observed. The picture will continue to change. In that way, the question of what these galaxies mean for us is also a question about the future. It is about what we will learn, what we will discover, and how those discoveries will shape the way we think about the universe and our place in it. There is a quiet continuity between the people who first looked at the night sky and wondered what those lights were, and the people who now analyze deep field images and measure redshifts, the tools have changed. The scale of what we can see has expanded enormously. But the basic impulse is the same. Look, notice, ask. Somewhere, right now, a telescope is collecting light from a galaxy that is so far away that its photons began their journey before the Earth existed. Somewhere else, a person is looking at an image of that galaxy, trying to understand what it reveals about the universe. And somewhere else, a listener is thinking about that chain of events, about the distance, the time, and the connection between a small moment of attention and a vast unfolding cosmos. All of these things are part of the same story. You do not have to take from that story any particular lesson or conclusion. It can simply be something you are aware of, something that sits in the background of your thoughts like a quiet, steady presence. The galaxies do not demand anything from us. They do not change their paths based on whether we notice them or not. They continue to move, to shine, to merge, to evolve, according to the same physical laws they always have. But our relationship to them can change. We can choose to see them as distant, abstract objects, or as part of a larger context that includes us, our planet, our history, and our curiosity. In the end, what all these galaxies mean for us may be less about finding a specific answer, and more about holding a particular kind of perspective. A perspective that can include both the very large and the very small, both the ancient and the immediate, both the complex and the simple. You can think about the trillions of galaxies, each one a system of stars and worlds, arranged across a cosmic web that spans the observable universe. And at the same time, you can think about where you are, right now, in this moment, in this place, under this sky. Both of those thoughts can exist together, without cancelling each other out. As the night continues, the stars will keep their slow, steady motion. The galaxies beyond them will continue their even slower dances. Light will keep travelling across space, carrying information from distant times and places. And here, in the quiet of the present, you can let that awareness settle gently, like a distant glow in the background of your mind, while the vast story of the universe continues to unfold, far beyond what can be seen, yet still, in a small way, connected to this moment of listening and rest.